Это?
Мгм.
Нет или?
Да, да. Мне лучше проверить в режиме просмотра. Да? Ну, нормально. Нормально.
Так, я ее скопировал. Можете забрать флешку?
Еще не закончилось, оказывается, пленарное заседание. Там же люди и на председатель. Вот он идет. Там доктор, что еще к этому. Он, в принципе, там закончил уже практически. Плач, телекоммуникация. Я туда звонил, вдруг забыл. Конечно, неудачно. Всех поблагодарил, потому что это было такой мажорный ноте. Но почему-то вас вроде все разделились, как это? Вот ты... Минус лох, лимит уже совершенно.
Можно попросить вот всех выступающих, у нас найдут трансляция, выступать за кафедру. Давай просто домой. Тут, в принципе, есть микрофон. Но если будут вопросы для зала. Раз, два, три.
Да. Слышно, да?
Погромче. Подольше второй.
Когда?
Да, желательно, чтобы садиться. Просто громко, так же голосом уверенно говорится, чтобы слышно было хорошо. GMO Salt 23. PowerPoint тоже у нас работает? Я знаю, я просто проверю, что работает. Все верно, да?
Yes, I think we need to start. Good morning. My name is Alek Antipov. I will be the presenter of this session. First talk of our session is new transparent spinel-based nanostructured glass ceramic with broadband absorption at 1.8, 2.4 microns. Olga Dymshits from Vavilov State Optical Institute, St. Petersburg.
Dear Mr. Chairman, thank you very much for your presentation, and this is the theme of my talk. Sorry. And I will talk about transparent spinel-based glass ceramics of zinc, magnesium, and lithium aluminosilicate systems doped with ferrous ions. And the motivation of this work was the successful application of zinc chalcogenides doped with ferrous ions. And we tried to search for other more environmental friendly and with better thermomechanical properties materials. And one of such materials is spinel. And it is well known that the tetrahedral coordination sites of spinel can be doped with transition metal ions with the oxidation state +2. So here you see the structure of the spinel crystal and among different reducing conditions. And is the ferrum iron-doped glass ceramics produced in reducing simultaneously with increase the crystallinity fraction of garnet crystals. We see the rays of the absorption band caused by ferrous ions in this phase. So in these glass ceramics, this goal was achieved. Then we studied the variation of the dopant content in the same glass ceramics, and we've seen that the Beer laws is obeyed here, which gives us the possibility to precisely correct the transmission in the desired absorption band. Then we studied the same materials produced in oxidizing, normal, and reducing condition. And it is interesting to notice that here is indeed the interplay of titanium 3+ and iron 2+ ions, and in strongly reduced conditions, the absorption spectra are in fact superposition of absorption of titanium 3+ ions in aluminum positions in octahedral of garnet crystals and ferrous ions in tetrahedral positions. And also you see that the proper choice of redox condition allows us to increase absorption associated with the ferrous ions in garnet crystals. And a very promising way to study the advantages and disadvantages of glass ceramics is the comparison of structure and properties of glass ceramics with those of a single-phase material. And in this case, we compared the properties of our glass ceramics with those of ferrous gunite doped ceramics. And you see that the X-ray diffraction patterns are very broad and have low intensity in our glass ceramics, which reflects the nano size of the crystals. Raman spectra shows the multi-phase character of our glass ceramics with the silica glass residual band and with the rutile band, while the absorption in the part of the spectrum which is interested for us is quite similar in both materials. The same was done in the magnesium aluminosilicate system, where the composition of spinel, it is a magnesium aluminospinel or a solid solution of magnesium aluminate. And here there is a difference with the previous system, because in zinc aluminosilicate system, gunite exists in the whole temperature range of crystallization up to 1300 degrees, while in magnesium aluminosilicate system, spinel has a limited range of stability. At higher temperature, it converts to magnesium aluminosilicate and then into a stable phase of cordierite. And here we see that the maximum absorption is reached at 1000 degrees centigrade, when there is a maximum content of spinel, and when with the formation of subferrine, where magnesium has a six-fold coordination and ferrous ions also.
Like in bulk form, they are like attached with multiple layers, and individual layers are quite stable, but these layers are attached with each other by weak van der Waals force. So we can simply separate them. It is possible to separate them, layers structure, and then they come in 2D form. So basically here in these transition metals, they are sandwiched between some sulfide or some chalcogenides. So one side this bond length is large, and one side bond length is a little bit small. So that's why they have huge anisotropy, and they are very good material to develop the polarization sensitive photodetectors. So in these material, especially TiS2 is one of the lightest material, and if we are talking about band gap, then TiS3 band gap is almost 1.01 electron volt, and TiS2 band gap is around 0.2 electron volt. So these material we can use in replace of silicon based technology, and these are very especially TiS3, it shows direct band gap, but in case of TiS2 it is known as semi metallic material. So first it's not working. Can you use here changing? We can change from here. Is there something?
Try again.
Yeah, fine. Thank you. So, in order to fabricate these material TiS3 and TiS2, we use chemical vapor transportation technique. In chemical vapor transportation technique, first we need to mix the material in required ratio. For example, for TiS3 we need 1:3, titanium and 3 is sulfur. And then we mix and we sealed in ampule, quartz ampule. And this is vacuum machine which used to create the vacuum, and then we heat it in normal furnace, maybe in CVD system. So as per what desired material we need, so TiS3 can be synthesized around 500 degrees Celsius to 550 degrees Celsius, and TiS2 can be synthesized and 600 degrees Celsius to 650 degrees Celsius. So by this technique, by chemical vapor transportation technique, we got material in powder form, and later we can further exfoliate it by creating dispersion of this material in some suitable solvent, maybe DMF, maybe NMP, or maybe IPA. So this is the basic characterization of this material. Titanium trisulfide is like a nano ribbon structure, where nano ribbon length is around 500 micron to 100 to 500 micron, and thickness is this width is in some nanometer. And this is the XRD spectra for a synthesized TiS3 nanostructure, and this is the Raman spectra. So in Raman spectra of TiS3, we can get mainly 3 peaks, Ag internal, and this third Ag internal, and fourth this Ag peak. So these are around 300 centimeter inverse, and 350 centimeter inverse, and 515 centimeter inverse. In case of TiS2, we used to get by this technique nano disc type structure. Although by changing the synthesized temperature, we can get some different structure also. And this is the XRD spectra for TiS2, and this is the Raman spectra. In Raman spectra, peaks are quite similar to TiS3, but here we get one special peak. This is called solder peak, and by the ratio of solder peak to this peak, we can get some idea about number of layers and thickness of this nano disc. So here some basic characteristics of TiS3. So this is the UV visible and IR spectrophotometer spectra, absorbance, and it shows multiple peaks from visible almost from UV to near infrared region, multiple peaks. So it can absorb the light in this broad region. So it's very good material to develop the solar panels and photo detectors. And here is the band gap study by Talkplot, and it showed in our case it shows band gap around 1 electron volt, 1.01 electron volt. And this is the thermal stability characteristics of TiS3. So TiS3 is quite stable material up to I think 250 degrees Celsius. After that, its phases are changes, and basically some sulfur vacancies start to create, and then weight start to reduce. So, but up to 250 degrees Celsius, fine, absolutely fine. And this is the basic properties of titanium disulfide. So, as unlike the TiS3, TiS2 also shows a broad absorbance like a broad solar spectrum. And in case of band gap, in which TiS2b synthesized, here is band gap is around 0.4 electron volt. And in case of stability, TiS3 is quite stable around 200 degrees Celsius. After 200 degrees Celsius, it's a little bit, its weight start to reduce. And so first, here in this slide, we can see how we prepare the photo detector or any solid state device which can be useful for photo detector as well as gas sensing applications. So we use dielectrophorese technique. So first we prepare that powder form material and prepare some dispersion of that material in DMF. And then by DEP technique, we deposit that material between the electrodes. Basically we align between the electrode, and electrode be deposited by standard lithography technique, and gold and titanium electrode used, and substrate basically silicon thermally oxidized SiO2. So here this is our first work, initial work on photo detector. This is TiH2 based photo detector, and I think in our best knowledge this is the on TiH2 based photo detector our group first time report any article on this topic. So first we analyzed the IV characteristics on different wavelength of light. We used LED light here, and we analyzed that sample from 375 nanometer to 1050 nanometer LED light. So we can see here as we change the wavelength, photo current, basically current is changed. And then we found like 450 nanometer it give highest photo current. So then we make a study with various power density of light, and it can detect very less power, 0.015 milliwatt per millimeter square. So here is that generalized graph like photo current dependent on wavelength. So as I explained here, 455 nanometer wavelength it give best photo current. And this is the with 455 nanometer LED light. This is the real time photo current graph with multiple cycles. And as we can see here, our graph, our this SW photo detector shows quite stable result. And as we change the power density of light, clearly like the current is changed. And the response and recovery time is also quite fast. Response is in this in case of TiH2 0.3 second, and recovery 0.18 second. And other parameters to analyze the photo detectors, that is like responsivity, quantum efficiency, and detectivity. These are also in such cases very quite high and comparative to reported work. For example, detectivity in 10 to the power 11, order of 10 to the power 11 Jones, and responsivity almost this is also 1.2 into 10 to the power 4. So it is also very high. Now this is the real time graph, photo current versus on different power density of light for different wavelength of light. So we can see in all case like from 375 nanometer to 1050 nanometer, it gave quite stable result. So after checking its basic photo detection properties, which we analyze the TiH2 based photo detector for different operating temperatures, so that our device can work in harsh climate, like maybe in some very cool temperature like Siberia, or maybe some hot weather like India, Rajasthan. In such type of place it can work. So for this purpose we analyze that SW device for different operating temperature. So we tested minus 150 degrees Celsius to 120 degrees Celsius. Of course, when we change the temperature, so current change, so that device can be work as a temperature sensor also. But here we tested complete device for 617 nanometer wavelength of light, and this is like a photo current graph on different operating temperature and different power density of light. So we got highest photo current around 0 degrees Celsius, and other parameter also follow almost same pattern. So let's see a little bit physics. TiH2 is known as semi-metallic material. So in semi-metallic material, especially in TiH2, when light incident, then some electron hole pair generate, of course, and hole trapped nearby the valence band edge. And this hole provided the localized electric field, which motivate the photo detection properties. So, but when we increase the temperature, then these holes start to detrapped from this energy levels, and due to this photo gating effect reduce, and that's why photo current start to reduce. Of course, some other effect also working here, like non-radiative recombination process, scattering process. So due to this also, this both side this photo current start to decrease. So these are some other parameter based on operating temperature in case of TiH2 based device. Like responsibility and quantum efficiency and detectivity. And especially detectivity is quite high, 10 to the power 13 joules, and which is very good as compared to reported data. So these are the real-time results for photocurrent on different operating temperature with multiple cycles. So like minus 120 degrees Celsius, minus 90 degrees Celsius, and 90, and means after that 120 degrees Celsius. And response and recovery time is quite fast. It is like almost we can say 5 seconds to 12 seconds. In this range, we got response and recovery time for this sample. And the good thing is that cutoff operating temperature we can enhance by increasing the bias voltage, because here majority of data is taken with 0.1 volt bias. So if we little bit we increase the bias voltage, then we can detect light even minus 180 degrees Celsius also. So this is the for TIS3 sample, same study, temperature based, with the 617 nanometer laser light, and with different power density of light. And TIS3 is capable even much lower power density of light as compared to TIS2. It can even detect 10 to the power minus 5 watt per centimeter. And this is the like photocurrent with respect to operating temperature. In this case, we got highest photocurrent around 330 Kelvin. So entire study is from liquid nitrogen temperature means 77 Kelvin to 548 Kelvin. And of course we tested other means parameter of material like resistance with respect to temperature. So initially resistance is high, similar to normal semiconducting material, and then resistance start to decrease as we increase the operating temperature. And photocurrent is also for up to room temperature. So first it is like a little bit constant type, and then sharply it increase in such a way. And this is the IV characteristics for different operating temperature, and with 617 nanometer LED light. And in such case, TIS3 giving very fast response and recovery. It is 0.093 second response time, and recovery is also 0.95 second. So, and quantum efficiency and photo responsibility, other important parameter of photo detectors device, these are also very high. For example, detectivity. Detectivity is very important parameter for photo detector device, and here we get almost 10 to the power 15 joules. And these are the some real-time graphs for different operating temperature from like 77 Kelvin to some 300 Kelvin for different this power density of light, and the remaining graphs are here for same series like 333 Kelvin and up to 543 Kelvin, I think. So now in this set of work we further analyze the TIS2 to develop some transparent device. So for developing transparent device, we made first ceramic gel, and then we added in our material TIS2 and TIS3 in different quantity. So here we can see in this stage, first we made alumina gel by using aluminum sec butoxide and DI water, and we heat it at 90 degrees Celsius with continuously magnetic stirring. After that we added HNO3 by drop in this solution, and further we magnetic stirred 1 hour, and then we added another these precursors like PBA, ethylene glycol and benzyl butapethylate, and then these all solution we put on reflux setup for 10 hours. Then we added in this our materials which we prepared, TIS2 and TIS3. So here in such case we added TIS2. After added TIS2, we deposit that freestanding thin film on one special cavity made on Teflon sample, 1 millimeter thick and some dimensions. So these samples are transparent, and here we can see it's a foldable and freestanding thin film, and by this technique we can deposit our semiconducting material, light sensing semiconducting material on large scale. So we can see this later we deposit on this electrode by shadow mask technique, and we can see on Samara University logo this our prepared flexible solid state devices. And then these are some basic characterizations of this material, like here this is SAM picture, and this is the AFM, and we can see, because I used here TiH2, so TiH2 is like nano disc structure, so we can see in this entire film homogeneously TiH2 is deposit, and this in SAM image also same thing is visualized. In this experiment, basically we conducted 3 experiments. One is with pure TiH2, and then 1 mg and 5 mg silver also be added, and we did systematic study. So we found, like we analyzed this sample with the laser light in near infrared 1064 nanometer, and we made comparative study. So when we added like silver in this 1 mg and 5 mg, then its photo current is enhanced basically, and these are all characteristics like real time photo detection, and these are like combined graph, generalized graph for photo current, and with different like samples. And here also, like response and recovery time is in the range of 0.2 to 1.6 second, and these are also giving very high detectivity in as compared to other flexible sensor. So detectivity is almost in 10 to the power 9 joules. And in this case, we took MOS2 in bulk, and then we exfoliate MOS2 in, I think, in DMF, and then deposit between the electrode just by drop cast technique, and then analyze just basic characteristics like Raman and SAM. Then we use for photo detection properties, and this sample is also giving in some seconds response and recovery time, and this is also be analyzed with LED light, and it is able to detect almost 0.05 milliwatt per centimeter square light density. In another work, we developed the photo detector on little bit high power density of light, like in watt, like 0.1 watt and 2.0 watt, and here only we made a study of resistance, how resistance of device is affect with respect to that laser light. So this is also a study, RGO based photo detector, and RGO we fabricated by modified hammer technique, and we tested for near infrared light, this photo detector. And this is one CNT based, of course it's not 2D material CNT, but we developed CNT based photo detector for visible light. And we also analyzed TiH3 for photocatalysis reaction to clean the water. Okay, just one second. Clean the water from toxic dyes like methyl orange and methyl blue, which is used in textile industries, to clean the water from that toxic dyes. So we use TiH3 in, I think, in very less quantity, 10 mg in 100 ml of water, and just in 5 minutes it was able, here we can see it is able to clean the water almost 80%, and in 10 minutes almost 93% water is cleaned from that dyes. And we make a study by taking absorbance, systematic study by absorbance, and light we use infrared in this, because TiH3's band gap is almost in infrared range, so that's why we use infrared lamp from here. Okay, thank you. Please question.
Thank you for the presentation. Question, please. Okay, no question. Probably. What is the main advantage of your photo detector in comparison with common photo detector in visible range?
It's like in photo detector, main thing is detectivity, how big signal it can detect. So our photo detector can detect very big signal like 0.05, and of course we are not from biology background, but we made a study. This TiH3 and TiH2 is biologically is not harmful, they are not toxic material, and we can develop this material little bit economic way, like with less price, and these materials stability is very high. And since especially TiH2 is like semi-metallic material, so it can work for broad range. Of course we don't have laser light for a mid IR or some far range, but we tested it almost on 10.6 micron and working fine till now. So we can develop with single material very broad range of photo detector.
Thank you.
Very short. Could you show your graphic dependence photocurrent from time?
Real time.
From time, yes. Or for example, this one, yes. Time is several seconds, tenths of second, and it's
No. It's 0.93 second. 0.093 second. Look here, 1 second. Yeah. Here.
For example, this one, yes. What
Yeah.
time? Minutes, it's
it
show
is like-
stability.
Yeah, it is for testing stability. Basically, one cycle is this only, na? So we can consider like 10 to 90% how much the current increase, na? From 10 to 90%. This is the response time we consider, na?
Yes.
So it is like in second or millisecond. range.
Milliseconds.
Yeah.
Okay, thank you.
Okay, thank you, speaker again. The next presentation, synthesis of direct line silicon-based thin transistors by using laser deposition technologies. Please.
Yeah. Okay, good morning, all of you. I'm Dr. Prachi Sharma. I'm from India. I'm associate professor in School of Electronics Engineering, Vellore Institute of Technology, Vellore. It's a #1 private university in India, just for basic introduction. So first of all, I would like to thank the organizing team of ALT23, and special thanks to the Professor Vladimir Pavliev to give me this opportunity for providing the invited talk. So today I'm gonna present a topic, realization of thin film transistor by using laser deposition technology. Yeah, it's changing here. We need to minimize.
Try again.
Yeah, thank you.
Maybe someone's
It's
battery.
changing here.
Another works.
It is changing here.
Something strange.
Can you pick that slide only? I'm explaining this. There it's not.
Does it change?
It's changing here.
That's strange. Why it's freeze?
Okay, so let's start. So today I'm gonna cover the basic introduction of the thin film transistors. So under that I will first discuss my initial work where we deposited the nanocrystalline silicon using electron beam evaporator, and later on we now started our work on MOS2. So we deposited that using pulse laser deposition, and then I will discuss the basic characteristics and the results which we got related to the MOS2 based TFT. So just give you an overview of the thin film transistor, that is also called as TFT. It's commonly used as a pixel addressing element and is a heart of large area electronics, means it is used as a switching transistor for the display applications like AMOLED and all that. So material that are commonly used by the researcher to have a active layer or a channel layer for fabricating TFTs are like, initially they started with the amorphous hydrogenated silicon, then polycrystalline, nanocrystalline, and nowadays we are working on TMDs. Such as MOS2. So if I give you an overview like why we switched to the MOS2, the thing is if I compare the amorphous and the polycrystalline silicon with respect to nanocrystalline, amorphous used to provide less electron mobility or uniformity. And also with respect to polycrystalline, this polycrystalline silicon is like I can say costly process to fabricate. So in that respect, we slowly moved to the nanocrystalline silicon. And then later on the TMD is MOS2. So why MOS2? Because first thing first, this mobelinite is abundant in nature, so we can easily use of that. And then as per the result, we found that it is easy to fabricate the MOS2 layer over the large surface area, which is the basic requirement for the large display. And second thing, we achieved better electron mobility, and the subthreshold slope also we checked. So we achieved steep subthreshold slope. So that's how we can say MOS2 is somehow showing better results. So again, if I come back to the TFT, so TFT is basically having 3 electrodes, source, drain, gate, and then the layer like gate insulator and thin semiconductor layer, which is also called as a channel or active layer. So as per the structure of the TFT is concerned, there are basic structures like top gated and the bottom gated. So these two is the example of the top gated, where they are further classified as a staggered at the coplanar. So in case of top gated, gate is obviously at the top side of the device. In case of staggered top gated, the source drain is on one side of the semiconductor layer, however the gate is on the other side of the semiconductor layer as per the fabrication structure is concerned. Again, in case of coplanar, all the source, drain and gate is on the one side of the semiconductor layer. Now, in case of bottom gated, the gate is on the bottom side, as you can see. So again, it is classified as coplanar and staggered. So that is structure of the TFT. Now, as I said, we started our work with the nanocrystalline silicon. So this is just to give you an overview like how we started. So first we did the deposition of 100 nanometer, 150 nanometer and 200 nanometer thickness of nanocrystalline silicon, and we characterized that layer by using FESM, Raman, EDS, all those things. And as per the process is concerned, as I said, we have used E-beam evaporator. So in case of E-beam evaporator, we all know that there used to be a electron gun. So within an electron gun, there used to be a filament where the electrons will boil off due to the presence of this high voltage, and they are targeted towards the ingot, which is presented here using a magnetic field. And then due to that, means once this electron will strike this ingot, obviously they will start boils off and they will melt. So they will create a wafer. That wafer is deposited on the top side of the substrate, I can say. So this is the general brief figure which I have shown for the 4 target E-beam evaporation setup. So this is related to the fabrication process, and as per the film deposition parameters are concerned, so these are the, so as you can say, process pressure is around 8 into 10 to minus 6 tons. So, and deposition rate that we achieved around 1.2 Armstrong per second. Now, if I just give you a brief overview of the results, so we we did the characterization like Raman, AFM, and FESM, and in case of Raman, we achieved the peak at 520 inverse centimeter, and then in case of AFM, you can see the uniformity of the nanocrystalline silicon, and as per the grain size of the nanocrystalline silicon is concerned, we achieved 5 to 6 nanometer around of grain size. So these are the results for 100 nanometer thick nanocrystalline silicon. Later on, we also analyzed the effect of the thickness, like 150 to 100 nanometer, and that we found that the nanocrystalline is growing as per the cone structure from bottom to top, so which verified the successful fabrication of nanocrystalline silicon. Then nowadays, we are exploring the new technique, which is pulse laser deposition. Like we are depositing MOS2 using pulse laser deposition. Now the question is, why pulse laser deposition? Because as per the literature survey, which is given as, if I talk about the exfoliation technique, so their advantages are there. Obviously, it's natural crystal of MOS2 is used, and then superior optical electrical properties are achieved. But the main limitation is maximum flake size is less than 100 micrometer. And as I said, we need a material which can be deposited over a large area for display application. So it is not good enough to have a exfoliation technique for industrial applications. So then, if I look into the CVD is showing good characteristic photoluminescence spectra, but the limitation again, as my colleague Nishan said, it's toxic byproducts, and inhomogeneous film texture used to be there. So we can avoid that. So if I now focus on the PLD, which is pulse laser deposition, so layer by layer growth can be done precisely by controlling the number of laser pulses. So this is very advantageous, like we can control the growth of the film, and then can also grow large area films which can be utilized for industrial purpose. So two of our main target is achieved. Now again, just for give you a brief overview, like why PLD, this is a literature survey which I found. So here, if I look into the basic techniques like PLD, exfoliation, and CVD, and all those that we are they used to achieve better mobility with PLD. So which is one objective which we can have. It's better in case of exfoliation and CVD, but we can see there is no saturation voltage, so we can avoid that. So at the end, somehow we concluded, okay, we can go with the PLD. So once we deposited the MOS2 using PLD, so these are the basic deposition parameter that we maintained. So excimer laser is used with a operating wavelength of 248 nanometer and the fluence range of 0.4 to 4 joule per centimeter square, and the pulse duration is 10 nanosecond. Now the idea here is the PLD technique basically is utilized to optimize the device quality MOS2 monolayer by varying the growth temperature and also the number of laser pulses. So these are the two parameters we are varying, and we are checking the control growth of the MOS2. So here, if I talk about the basic deposition parameter, the base pressure is maintained at 1 into 10 to the minus 6, and the substrate temperature is checked at 600, 700, and 800. For all the three temperatures, we check the results. So monolayer were deposited on passivated silicon substrate, where a 300 nanometer SiO2 is first grown by using basic thermal oxidation technique on a silicon wafer. Now here, we are using the silicon as a substrate, which will act as a backgate. For if we go for the thin film transistor, as I discussed, the bottom gate having the back side of the structure. So this silicon substrate will act as a backgate. So that way we are processing. Now, if results are there, the Raman spectroscopy analysis is first carried, and there the peaks are, as you can see, the peaks are at, we are getting two peaks, E12G and A1G. So they are at around 380 and 405. So peaks corresponding to E12G and A1G Raman phonon modes were observed. And in Raman spectra of MOST film deposited at various temperature, that is 600, 700, 800 are visible here. And if we'll talk about the wave number difference, it is coming around 25 centimeter inverse, and which resembles the basically the bulk MOS2 production, and it is reported in the literature. So now one more we can say, if I look into the Raman shift of the deposited MOS2 layer at 700 and 800 degrees centigrade. So in case of 700 degrees centigrade, we can see there is a little broader peaks of E1 to G. However, it is like high intensity peaks, which is for A1G. Similarly, this is like more, this is for 800 degrees centigrade. And here also you can see for different layer, that is like if we are maintaining the number of pulses as 50, we can achieve mono layer, 70 bilayer, 100 tri-layer, and 150 quad layer. So we varied the temperature, we checked the results, and also we varied the number of pulses, and based on that we can conclude like there is a slightly broadening of E1 to G peak and lesser intensity compared to A1G modes. And if I go into the physics of that, that may be due to the amorphous nature of the substrate, which is silicon in our case, so which provides surface scattering for the incoming MOS2 species. And now, if I look into these results, which are for different temperature, so here also you can see the A1G peaks are increasing like 405 to 408, and here also 379 to 383. So it is increasing, which shows the high crystallinity. If we are increasing the temperature, the crystallinity of the film is increasing. So the reason behind that, maybe this will attribute to the fact that if we increase the temperature, the nucleation energy barrier gonna decrease, which will higher the nucleation density, and this will lead to the higher crystallinity. So this is the basic findings. And then we checked for the full width half maxima, and there we check the different pulses like 50 to 150, and here we can see it is decreasing if we are increasing the number of pulses. Like from mono layer to quad layer, the E1 to G peaks is from 8.61 to 849. Okay, so the values are decreasing with increase in thickness, and this is maybe due to the fact that there is a lesser surface scattering experienced by the higher thickness. So if we go for the quad layer, there is a lesser surface scattering, which will somehow give us the lesser value for the E1, 2G and A1G. Next, we have a result of HR-TEM. So here the results are shown for the tri-layer MOS2. So the thickness which is achieved is 1.96 nanometer, and it's a tri-layer MOS2. As you can see from here, this is the tri-layer formation which is there. Then the AFM results. So here the very first graph is actually to just analyze the root mean square roughness, which is coming around 0.4 plus minus 0.1 nanometer, and then obviously it suggests the smooth morphology of the MOS2 monolayer, which is deposited on the SiO2 substrate of 300 nanometer, means SiO2 and silicon substrate. And here the second figure, it basically you can see there is a discontinuity between the image. So this particular line showing the interface of the MOS2 monolayer and the uncovered SiO2 silicon substrate. Now coming back to the next AFM results, here this figure basically showing the thickness profile, which is coming around 0.72 nanometer. And if I talk about the average grain size, we checked with the three grains. One is 32 nanometer, 36 and 34 nanometer. So we are getting somehow uniform results, which is from 32 to 36 nanometer. So higher quality of MOS2 is present in the present case is attributed to the optimization of growth temperature, and one more factor is due to the nitrogen, which is presented as a background gas during the deposition of MOS2 layer. Now next, if I now talk about the application of MOS2 based TFT, so here as I told you that silicon substrate will be used as a backgate, and then we have a SiO2 layer which is of 90 nanometer, and here we have a MOS2 channel. These are the terminal source drain terminal. So this MOS2 layer, which is deposited by the PLD using the 100 laser at around 800 degree centigrade is used here, and the electrode is used like gold and the silver, which 50 by 50 nanometer as a source and drain metal, and 90 nanometer thin SiO2 as gate active, which is grown on the silicon wafer. And here silicon is used as a backgate. So if we look into the characteristic of the thin film transistor, so very first characteristic, which is IDS versus VGS, is shown here. Just from here you can get the idea of the threshold voltage. So as you can see, the threshold voltage is minus 2.64 volt, which is achieved. So at VGS of around 0 volt, the fabricated transistor are normally on, indicating the conduction of electron in the accumulation region, which is caused by the positive trapped charge carriers in the charge carriers which are present in the SiO2. And it concluded the good ion and I-off ratio of around 1.4 into 10 to the power 5. Now the fabricated backgated device shows N-type unipolar behavior also, and it is on for the positive gate voltages. However, it maintains off state in negative VGS range. This particular second graph is between IDS versus VDS. So here the VGS is maintained between positive 2.5 to, sorry, it's a mistake, minus 2. Okay, here it is. So minus 2.5 volt to plus 2.5 volt VGS is maintained in the accumulation region, which shows the saturating behavior at high value of VDS. You can see here it's showing the saturation behavior, which is crucial parameter for 3D ICs. And if I talk about the display, so it is practical for practical display devices. These are the critical parameters. Now next, the two main parameters which we checked for the thin film transistor is, first one is the subthreshold slope, and the second one is the electron mobility. So if I talk about the subthreshold slope, we all know that it's an important parameter, as a device exhibiting steep subthreshold slope allows faster switching, and it's highly required for the display application. So that is what we checked. So subthreshold slope value is measured around 360 millivolt, and the obtained value of subthreshold is relatively low, indicating the realization of fast switching transistor. So this is just a Jana formula which we used for the calculation of subthreshold slope, where C int is the interface trap capacitance and CUX is related to the gate oxide capacitance. Now next, this is just a last slide. So next is effective field effect mobility. So we all know the basic formula of CUX, that is what is used. CUX is equals to epsilon OX divided by TUX. So if I talk about the TUX is maintained at 90 nanometer, and these are just general value for SiO2. So as per the calculation, the CUX is calculated as 3.83 into 10 to the power minus 8. Farad per centimeter square. Now the estimated value of the interface trap density means, if I talk about D internal, so which can be calculated as C internal divided by the charge, so it is coming around this value. If I put these all values in the to calculate the field effect mobility, the field effect mobility is coming around 44 into 6 centimeter square per volt second, so which shows a better mobility. And we can conclude here that as per the results which we got for the subthreshold slope and field effect mobility, we can say this particular MOS2, which is deposited by the PLD, is a efficient material, or is a efficient technique to have for the fabrication of display devices. That's all. Thank you.
Okay, thank you for the presentation. Please, a question. Okay, no question again. Maybe my question. Please, non-chloride or another laser.
Okay, so the main reason is the availability in our department. So we went through this pulse laser deposition. So the particular laser which we have used is available in the institute. So that's why we proceed with that. So based on the availability, we are still working on it. As you said, there are other possibilities, so we are still working on it. Maybe in future we'll give you the main comparison between all those things. Yeah. And
okay, thank you again.
Да, не знаю, возможно, статикой, что ли, ударило. Сейчас это разберемся. На сколько сейчас перерыв будет? Ну, 10.
До 50 минут сейчас.
20 попробую сейчас исправить. А, флешечку вашу.
У вас сбои постоянно. Может быть, надо попробовать сейчас всем. Да? Постоянно. Что-то пробило, говорят.
Возможно, статика пробила. Тут на хабе все просто было.
Ну,
Сейчас попробуем
да,
исправить.
просто как вы запускаетесь, он вроде идет нормально. Каждая новая презентация.
Да, да, вот интересно.
Линия снизу только сейчас была, то есть какие-то...
Леди, это проектор. Так,
Калибри называется.
так, сейчас, секунду, проверю.
Сейчас. Мне надо один только номер, чтобы был. Там number one very.
Один, да?
Сейчас, погодите. Сейчас, подождите, где? Калибри, вот оно, да? Калибри. Вот калибри, вот.
Да, калибри, вот, Origin A and T. Крекс.
Да,
Вот оно, да.
Сейчас к выводам давайте глянем, я посмотрю та версию.
Секунду.
Можно?
Да, как раз попробуйте.
Так, да, вот как раз мне на пару. То есть вот такой штучкой буду переключать, да? Нет, это вы мне дали лазер, да?
Это лазеры.
Ага.
Опять не
А
стоит?
переключать? Вот эта стрелочка, да?
Это вперед, а с другой стороны она назад.
Ага.
С другой стороны стрелочка.
Хорошо, я хочу дойти до конца просто.
Да, проверь.
Ага, я сейчас проверю. Да.
Да, проверьте. Там,
Так,
вообще, там еще
ой, вот все-таки R у меня там. Ну ладно, radio. А что ж такое? Я же вроде поправила. Тут я уже не поправлю. Ну ладно, все.
Никто не забудет.
Да нет, ладно, все.
Не, ну-
Нет, у меня есть PPTX. Не,
презентация запустилась.
так, сейчас вот она.
Мышка есть, если... это-
Сейчас, слушай, Игорь, я там добавила пункт вывода, но почему-то он у меня не спасся так, как надо.
А может вы другой где-то
Ну,
сохранили,
ладно.
нет?
Да, может быть, там самое последнее надо посмотреть. Там ток должен быть.
Ток?
Ток, ага. Так, сейчас ток, вот здесь, вот здесь, вот, там где один. Мгм. Так, как мне на последнюю страничку сразу перейти? Так. На последнюю, да?
Это-то?
Да, вот эту, ага. Последнюю минуту увидела, что главный вывод пропустила.
Тут уже никто не замечает.
Да я быстро там все пробегусь. Лазер работает. Ага. Все, вы топик поставили, да?
Да, ту.
Ага, хорошо.
Переключать вот это вот.
На... Нет, вот смотрите, нам этот...
Вот.
На кликере, сейчас покажем.
Вот это. Она здесь
сейчас
не
подожди.
работает ничего.
Да ладно, сейчас проверю, сейчас поставила.
Так, это ваша, да,
Так,
флешка
давайте,
белая?
да, давайте я. У вас тачскрин тут, что ли, да? Тачскрин?
Нет, вот, ну, тачскрином вы хотите мышкой. Удобнее будет. Стаканчик с водой, да, ну, в принципе, куда-нибудь слева, если поставите на стол, он никому мешаться не будет.
Так куда перетаскивать просто на рабочий стол, что ли, да? Презентацию куда девать?
Презентацию там, давайте помогу.
Вот презентация 19.09.23. Так, давайте я, может быть, назову свои, а то не найду потом. Давайте Антипов напишем. Нет, переключить надо. Ну ладно, это, в принципе. Ага. Окей, и давайте запустим, потому что там один эффект есть, я не знаю, пойдет он или нет. Так, а давайте, значит, переключать. Вроде идет.
Работает?
Ну, что-то, да, он
Анимация, да?
Да, анимация вроде работает, да, это хорошо. Если я флешку вытащу, она будет продолжать работать, да, там иногда эти файлы нужны, которые...
Ну, просто скопировали сейчас.
Там же они прилагаются, не просто.
Ну да, я сейчас попробую вынуть флешку, да, и проверим.
как она будет работать без файлов, если они не
Ну,
слышат?
не, я не знаю. То есть они как-то, может, как-то они, может быть, там подгружены. Так, указка это вот это, да? Ну, в принципе, понятно. Так, могу я вытащить флешку туда или...
is about 1% of the intensity generated by the laser. You could have instead of chaotic pulsations, you could have regular patterns, stripes and hexagons, for example, for different values of injection. And also you for critical value of injected field, you could have a completely stabilized output beam. This critical value could be calculated analytically from the parameters of our model. So it is important to make some numerical simulations and to take into account the real profiles of the pump and external optical radiation. So we show that in the real situation, external optical radiation without injection leads to chaotic pulsations, and with optical injection we see the stable output pattern. Also, it was important to investigate the influence of detouring between the injected and generated field, because in experiments it is impossible to take equal of two with frequencies because of some technical problems, and we show that incoherent optical injection also leads to stabilization of output laser radiation, but we need some more injected field. Those results were published in August 2023 in Optics Letters, and you need to retrospect and what it is. Thank you for attention. Do you have any questions, please? Okay, no questions.
So now I would like to welcome Dr. Vismeta from Proctor General Institute of Russian Academy of Science.
About highly transient simulated ground scaling with combined trackers shift and crystals and local stuff in proper this outline, introduction, introduction, problem, possibility to solve, laser systems and crystals under study. Experimental results of simulation around spectrum and conclusion. Okay, motivation. Multi-wavelength ultra-phosphorescent sources in a range of 1,000–1,300 nanometers are of high importance for multicolor
2-photon fluorescence microscopy of living tissues. Recently, such sources have been developed on stimulated Raman scatter using complicated systems of synchronous 30-second laser pump, simultaneous excitation of several fluorophores can increase depth and contrast of three-dimensional imaging of living tissues. However, development of simple single-pass nonlinear converters for multicolored ultra-fast laser pulses with duration of 1 picosecond and shorter remains an acute problem. Highly transient stimulated Raman scattering with combined frequency shifts on stretching and bending vibrational modes of crystals with tetragonal symmetry can solve the problem. Figures show possible conversion using sub-picosecond pump laser, conversion in tetragonal crystal with combined frequency shift, with short shift on the bending mode and long shift on the stretching mode. So we will have many Stokes components of radiation in the desired range from 1000 up to 1300 nanometers. The fact is that transient stimulated Raman amplification increment is proportional to the cross-section of Raman line. It is product of steady-state Raman K coefficient and length of the Raman line. So lower intense bending mode of the crystal can be not so bad for Raman scattering if the pulses are very short. So the stimulated Raman scattering is transient. Another important characteristics is effective interaction length. For short crystals, it is temporal Volkov length. It is pulse duration divided to the group velocity mismatch, GVM. So for lower shift Stokes components, we have a longer effective length of interaction. It can help to realize simulated Raman scattering not only with long shift, but also with short shift. But we have a problem of cell phase modulation, suppressing simulated Raman scattering. If the pulses have a peak power higher critical power of self-focus. The figures show recent results from Lebedev Physical Institute. The barium tungstate crystal, short crystal, was pumped by sub-picosecond laser, and they had supercontinuum generation instead of stimulated Raman scattering. How to solve the problem? If the peak power of radiation is higher than critical power of self-focusing, we should use weak focusing and enough long crystal for increasing the interaction length at filamentation. If the focusing is weak, threshold of filamentation is lower than a threshold of breakdown. So we checked no breakdown in the strontium molybdate crystal in conditions of our experiment at focal length of the lens at least 80 millimeters. Second, we should use controllable chirping of pump pulses for compensation of a chirp of cell phase modulation. Figure at the bottom show that a transform limited pump pulse leads to a blue shifted Stokes pulse by cross-phase modulation from the pump. So adding a negative chirp to the pump compensates for self-phase modulation and removes the blue shift from the Stokes pulse. Laser system. Experimental setup, we used sub-picosecond terbium pump laser, Antaus, produced by Avesta. The wavelength 1030 nanometers, pulse energy 40 microjoule, transform limited pulse duration of 0.25
the only person in
picosecond.
this conference.
The pulse can be stretched up to 6 picoseconds using positive or negative chirp. Very good beam quality. We focused radiation to the Raman crystal under study and measure characteristics. We used 5 crystals. All the crystals were grown at our institute, Lyudmila Ivleva group. All crystals have high beam, high optical quality, large size. So we used crystals with 6, 7, and 8 centimeter length. Okay, calcium-containing crystals, calcium vanadate and calcium molybdate. You can see simulated spontaneous Raman spectrum. You can see high intense stretching mode and low intense bending mode for each crystal. Bending mode is lower intense. In calcium vanadate, we have equal line width for the stretching and bending modes. And so integral cross-section for the bending mode is very low in comparison with that for stretching mode. For calcium molybdate crystal, we have bending mode wider than the stretching mode. So integral characteristic is not so low, but lower than for stretching mode. Okay, we studied also strontium containing crystals. These are strontium molybdate and its solid solutions with strontium tungstate with different contents, 80-20 and 50-50. Strontium molybdate has very wide bending mode, 4 times wider than stretching mode. So integral characteristics for the modes are close to each other. But for bending mode, it is slightly lower. In solid solutions, we have interesting situation. Molybdate and tungstate bending modes have very close frequencies. And so we have one combined bending mode with very high integral characteristic, higher than for stretching modes. We have 2 stretching modes, one stretching mode for molybdate and one stretching mode for tungstate. For 50-50 content, we have equal intensities of stretching modes. So we have many ways of Raman, simulated Raman conversion. Okay, experimental results. In calcium-containing crystals, figures at the top show spectra of output radiation, panorama of all measured components of radiation. Figure at the bottom show high resolution spectra of output radiation, but only for first Stokes component with short
shift and with long shift on these vibrational modes. What we can see? We can see discrete lines of stimulated Raman scattering, Stokes components, and pedestal of supercontinuum. Pedestal is higher intense if the pulse is shorter. It is interesting that negative chirp of pump pulses resulted in higher intense stimulated Raman scattering. It can be explained by compensation of positive chirp of cell phase modulation. In calcium vanadate crystal, we had only long shift Raman conversion on the stretching mode because bending mode has very low integral cross section. In calcium molybdate, we had not only long shift conversion but also short shift conversion. This is first Stokes on bending mode, but with low efficiency. Strontium molybdate. We can see for this crystal, we can see high efficient stimulated Raman scattering on both modes, stretching and bending modes. We can see that total Raman conversion was up to 48%. Negative chirp is better for positive chirp. You can see also photos. Photo at the top, spots of radiation decomposed by the diffraction grating. Photos at bottom, filaments inside, and lightening of output phase of crystal by anti-Stokes conical emission. We can see that filament is longer and is brighter if chirp is positive. It can explain higher efficiency of Raman conversion at negative chirp because we have low losses to the supercontinuum generation in this case. Solid solutions. We can see very efficient Raman scattering, essentially with short shift on the bending mode. So we obtained up to 6 components in the desired range from 1000 up to 1300 nanometers for the 50-50 solid solution. Interesting is that interesting situation that long shifted Stokes component is combined with 2 shifts in molybdate stretching mode and tungstate stretching mode. So line width is wider than for pump laser, 2 times wider. So it is interesting to obtain pulses shorter than transform limited pump pulse. We measured also pulse energy for each Stokes component. Here you can see measurement only for first Stokes components with short shift and with long shift. What we can see for different crystals. Calcium vanadate. Calcium vanadate had scattering only on stretching mode, long shift, with energy of about 3 microjoule, not higher. Strontium molybdate, on the contrary, had the highest output energy of stokes with long shift, 10 microjoule. But 2 microjoule energy in short shifted stokes component was obtained too, but it is low. For strontium containing crystals, we have higher energy for short shifted Stokes components. The best crystal is 50-50 solid solution. We obtained higher than 7 microjoule output pulse energy for short shifted Stokes component. And also we can see that conversion into short shifted Stokes was in the optimum range of pump pulse duration of about 2-3 picoseconds. It is because it is between dephasing times of bending and stretching modes of about 1 and 3 picoseconds for the crystals. So conclusion, for the first time to our knowledge, we have demonstrated highly transient, multi-wavelength, single-pass stimulated Raman scattering with combined frequency shifts on 2 Raman modes of different crystals in conditions of competition with self-phase modulation. Up to 6 spectral components of output ultra-fast radiation with a low wavelength spacing in the desired range of 1,000-1,300 nanometers were observed in the 50-50 solid solution of strontium molybdate and strontium tungstate, which is the most intense bending vibration mode than the strontium molybdate. Negative chirping of pump pulses was better for efficient Raman conversion due to compensation of a positive chirp caused by self-phase modulation, with total Raman conversion efficiency of up to 56% for the optimum solid solution, strontium molybdate, strontium tungstate. Pump pulse duration being intermediate between the dephasing times of the stretching and bending vibrational modes were optimal for Raman conversion into the optimum 50-50 solid solution of strontium molybdate and strontium tungstate. Okay.
Thank you for introduction. My talk is the overview of activity of our team for testing of laser induced damage in mid-infrared laser crystal, linear crystal, and 2-micron laser application. First of all, it's well-known motivation for development of powerful, efficient mid-infrared laser. High efficiency and compact mid-infrared laser have a wide variety of applications for medical, for LiDAR sense, control manufacturing, molecular spectroscopy, scientific applications. We demonstrate spectrum of gases and explain application of molecular gas detection. Medical diagnostics, industrial this is also an application for to strong water against absorption in mid-infrared to have good surgery. LiDAR application so very wavelength range. So there are also special applications, and we have a wide variety of applications. Powerful mid-infrared laser source summarized in this figure. We have quite powerful gas laser, two laser, we have diode laser using quantum cascade laser. However, we have a lot of solid state laser based on night crystal doped by chromium and iron ion. We have novel fiber laser based on night right fiber, and we have optical parametrical scatter fiber. State of the art of this technique is solid state laser based on the night crystal have the power up to 150 watts at two souls per random pulse mode, multiple pulse at target wavelength. And optical parametrical oscillator, most powerful moment, we have up to 160 watt in the peak pulse nanosecond mode, and of about 200 nanosecond pulses with low repetition rate, practically important from 3 microfarads. However, unfortunately, the scaling of the edge power pulse by laser diffusion. Laser geometry is the most important problem for solid state. And we try to investigate different kind of material by using the same technique. And we have studied non-linear crystal, barium crystal, night crystal, and special night glass. Continuous wave from fiber laser, wavelength, and we pass gold laser 2000. Let us technique laser, lamp, splitter, quite technique, use different procedure for characterization of method so-called one-on-one method, S-on-one method, and R-on-one method. Several methods derived by standard, and the main point for this method. In this method, each site goes on single laser. In S-on-one test and closed test created by series of pulses. However, if we have material limited average, we cannot use a big group for moving power. In this case, we use so-called R-on-one test. Selected site was detected by N pulse after moving of the sample. We tried to study geometry in our plate. Then first study material, very important crystals, the GT crystal, crystals due to very good absorption properties and very high nonlinear coefficient, very good conductivity. In this moment, the GT crystal is the most important crystal for powerful optical parameter amplifiers. This material produced in Russia, in Tomsk, and we try to compare this material with Chinese material from Harbin Technical University. And we try to compare different material with different properties. Material mechanism for laser-induced damage on the surface of high purity ZGP is the crystal lattice defect, imperfect surface quality, and morphology of anti-reflection coating. We have studied the different impurity and different problem with volume of our crystal, and most important problem is for high purity crystal is the dislocation inside the volume of our nonlinear crystal. This dislocation gives us a problem with decreased damage of our crystal, and one of the most important problem is the decrease of concentration of dislocation of the nonlinear crystal. The next talk, very important point, is the surface defect and pollution parameter of nonlinear crystal. Even nanometer size homogeneity in the surface of our crystal give us strong decrease the laser-induced threshold. So we need to have very good pollution, and our colleagues from Tomsk and from Samara try to use different pollution techniques. One of the most interesting pollution approach is so-called magnetorheological pollution machine that can give us scale of homogeneous below nanometers. Very important point for laser-induced damage is the anti-reflection coating of the surface. And manufacturers from Tomsk also try to study different kinds of materials for pollution, for coating of the crystal. And in that case, it's possible to see these materials as most effective material to decrease to increase damage threshold. Laser irradiation parameter also gives strong influence for the laser-induced damage. Practically all parameters. I mean, not only fluence and intensity, but also repetition rate, pulse duration, exposition duration. It's also important. Even beam diameter. All these laser parameters very important from the point of view of damage threshold. In our case, we have nanosecond pulse duration with kilohertz repetition rate, but we have our repetition rate from 10 Hz to 100 kHz. And in this repetition rate area, in any case, we have the problem with laser-induced damage threshold. So for low kilohertz, for low repetition rate, we have measured increase but for high repetition rate and for high exposition duration, laser-induced damage threshold. It's possible to see the interesting figure time lapse of optical damage track in ZGP provided by digital holography with broadband camera. It's possible to see that damage area moved from output surface to the input surface of our sample. In our case, damage was always in shade on the output surface of GGP sample, and not only in all our measured material with high purity. We have problem with surface initiation and output surface. Most dangerous point for induced damage due to little bit more field in this boundary in comparison with input phase of the plate. Unfortunately, the GP damage take contribution for optical parametric oscillation. Even below threshold of laser damage, we have measured power drop of optical parametric due to induced absorption. It's very interesting that below threshold, this is a reversible effect. It is some kind of reversible photodactyl in however, above change reversible. So the next test is the also important crystal, novel crystal, barium, gallium, selenium, and barium, germanium, selenium crystal. This crystal was produced in Kuban State University. It's an important crystal for application by using not only 2 micron quantum beam but also 1 micron beam. In our case, we tried to study laser-induced damage at 2 microns. And in that case, we have measured again very strong damage, and even damage threshold was measured at lower in comparison with the crystal, even at low repetition rate of 1 kilogram. It's possible to explain quite poor thermal conductivity of this material and its limit of the application of this crystal. The next point is the study of laser crystal. It's selenite material doped by chromium or iron 2+ ions. In that case, we have again the influence of different parameters. And in our testing procedure, we used 2 micron laser. And in that case, lower damage threshold was for chromium doped selenite crystal. It's easy to explain because chromium doped material have quite big absorption at 2.1 micron, and in that case, threshold of laser-induced damage lower than for selenite, undoped selenite, and even for iron doped selenite. And the last point of our testing, last point of my presentation, is a special high purity chalcopyrite glasses. These glasses it's used as cladding glasses for chalcopyrite fiber. It's not core glass, but it's a glass for core, as I understood from explanation of Professor Shiryaev. In that case, we used thulium, continuous wave thulium doped fiber laser at 1.9 micron. And in that case, we have measured again the laser-induced damage, but we have not pulsed regime. We have continuous wave radiation with characteristic pulse with exposition time of several seconds. And in that case, we have measured damage of our material. It's very interesting that the measured damage threshold was for these two glasses was less than well-known arsenicum sulfide glass. It's very interesting that this glass had very good damage property in comparison with novel glasses. This problem can be explained not only impurity, but maybe more problem for tendency to crystallization of these glasses. And in this case, the crystalline phase give us decrease of laser-induced damage threshold. And to summarize my talk, laser-induced damage for all materials is very important. However, we have different value, different number of fluence or intensity for different repetition rate. And this crystal at the moment is most successful crystal from the point of view of laser-induced damage. And last year we have improvement of this parameter, not only in Russia but abroad, in China, in the United States. It's possible to hear some information about improvement quality of first of all the GP crystal. And in principle, 6 joules per square centimeter. It's very good fluence for the optical parametrical devices. And prospect for improvement of this parameter by improvement of the crystal quality, polish on surface, anti-reflection quality. This work was done in collaboration of my group from Institute of Applied Physics with manufacturers from Tomsk State University, from Chinese group from Harbin, from Institute of High Purity Substances group of Dr. Balabanov and Professor Shiryaev, and in collaboration with group from Novosibirsk State University and crystal manufacturers from Kuban State University. Thank you for your attention.
Anybody have questions? Much for the very interesting report. I would like to know how many crystals, how many samples of each crystal you have studied, and do you have some statistics concerning the samples?
It's a good question. In principle, we used different number of material, different number of plates. We used for the GP crystal. We use different plates, different number of inclusion and dislocation. It was a special statistic procedure. A statistic procedure in our case, averaging was for the sites up to 500, for example. Statistic, but for other material, for example, for the glasses, we have smaller aperture, and in that case, we have approximately 10 different sites. So it is special. The damage is statistical behavior. Of course, we need to have the average.
Very, very good talk. Can I ask you about this fascinating movie that you showed, how this damage front appears, and how exactly did you take it? Because if it is just near the edge, then the threshold can be somehow initiated by this extra surface. Can you comment on this?
The question about why the output.
The first half of the question is how did you take it, and then
How did you? It is a special technique for visualization. For visualization, the volume inside the plate, so-called the digital holography technique with broad camera. I have not additional figure for explanation, but it's possible to see in our published paper.
Go deep into the sample with this technique, or you have to be near the surface?
The thickness of our studied sample was different, and in principle, it's possible to see the similar behavior in a small thickness plate with thickness of about 2 millimeters. But also the similar behavior is possible to see in the sample with 20 millimeters. For example, is a universal behavior. It's not so important for the point of view of the thickness. Maybe more important parallel of but in any case have approximately the same behavior.
Right. Thank you.
Please show.
For the finite glasses. This one. Do you mean with glasses? Yes. In this figure.
So now I would like to welcome Dr. G. Buffet from Prokhreb General Physics Institute of Russian Academy of Science.
Origin of radial and tangential cracks in optical fiber performance. I'd like to tell you about residual stress in fiber performance, cracking in the process of manipulation with performance in cold, at cold temperature, room temperature, star in process of perform manufacturing at high temperature, and our new results in measuring in determination of refractive index of the melt core of the preform at the process of its manufacturing, and connected with it stress of very high value of about 20 gigapascal, which could be reason for the radial cracks, so-called stars appearance. The typical fiber preform are in dimensions and reflecting cladding of pure silica and core cladding which consists of doped silica. The material of doped core and pure silica differ from each other by coefficient of thermal expansion. And the temperature of manufacturing the preforms is very high, of about higher than 2000 degrees centigrade. And so when at room temperature, the difference in the coefficient of thermal expansion leads to residual stresses. At room temperature, the residual stresses usually are tensile. This is an example of stress element which is preformed, which is used for panda type fibers, and even here in the very stress preform, the level of stress is only 50 megapascal. That is view of transmitted white light optical image, and the level of the pressure of the stress could be determined from the photo in cross polarizers. But even this level of stress is sufficient to start the process, to start the cracking of the preform, that is the same preform here, which was shown previously before cutting. And when it was cutting by the diamond blade. And the second example that is performed with a low level of residual stresses. And you can see that both of them, the form of cracking, contains the annular component of the shape of the cracks. And it is known from this reference that in cooling process, the annular cracks arose when the coefficient of thermal expansion of the core is higher than of the surrounding material, and they are radial when the coefficient of thermal expansion in cooling process are lower than of the surrounding material, and the direction of the cracks are perpendicular to the direction of tensile stress. And the radial stress usually is the process of manufacturing of preforms. You can see here the example, several photos of heavy doped by germanium or aluminum silicate preform. And from our point of view, it looks like you can see branching of the cracks and filling them by the material of the core, and penetration of the cracks into the cladding. And from our point of view, it looks like a molten core under high pressure cracks the cladding, and thus origin in that way. But there was no experimental support for this model, for this idea, because there was no experimental data during the cooling process. And in this work, we obtained experimental data. So in the process of cooling of the heated preform, we determined the refractive index of the core. The preform was heated in the MCVD lathe, and intrinsic thermal radiation of it serves as a probing radiation. There are two important points which are necessary to use this method. That is, if we compare the transmitted light, angular pattern of transmitted light from Fresnel equation of two polarization, we can notice that the difference between them has the maximum, and the magnitude of this value is almost linear function on the relative refractive indices of the contacting media. So if we know the amplitude of this maximum, we can determine the refractive index, relative refractive index. And the second point is that to obtain the angular diagram, it is sufficient to take a photo in paraxial beams, because if you compare this to photo, you can see that due to axial symmetry of them, these two schemes are equivalent. And so we developed this method and use it. This is our optical scheme. That is sample, polarizer, telescope, and camera. We use for our measurements two preforms. One of phosphosilicate preform with a low level of doping, and the second germanium silicate preform with heavy doping. You can see stars here, and that is side view, that is cross-section view, and that is profile of refractive index of the core at room temperature. And the next, that is photo after the heating of the preform, and then it was cooling. And we measure, take the photo, and we measure, and we determine the distribution of from the photo, the distribution of intensity of transmitted light of two polarization, and the difference is quite pronounced on the boundary of the very bright core and platinum. And the value of this maximum enables us to estimate, to obtain the value of refractive index, and it is very high. It is 1.64 for phosphosilicate preform, and 1.75 for germanium silicate preform. And with this process, the change in refractive index depends the most from the pressure within this material, and from the literature data, we find that the pressure which is connected with so high value of refractive index is 30 gigapascal for the germanium silicate preform, and 15 gigapascal for the phosphosilicate preform. And the theoretical damage threshold for the glass theoretical is about from 10 to 30 gigapascal. That's here. And in experiments is measured as 18 gigapascal. And now the conclusion. The angular diagrams for solar radiation enables to determine the refractive index of the core, the molten core, and that is 1.6 for phosphosilicate and 1.25 for germanium silicate preform, and corresponding value of the pressure are 15 and 30 gigapascal. And so we obtain the support to our model that radial cracks can be interpreted as a still calculated destruction under the action of the extra high pressure in the core. The stars was studied many years ago, but in models, there are several models, but no one of those models is sufficient to explain so high difference in the refractive index and so high pressure. The obtained knowledge can be useful for control of manufacturing process of fiber performance, and also it is
Anybody have question? So now I would like to call Dr. A.Y. Jensen from South.
Thank you for introduction. Um, Recently, rare earth borates are intensively investigated as potential functional material for luminescence and nonlinear optical converter. This attention is due to their unique optical properties and easy of preparation and diversity of crystal structure. Recently, we reported two new samarium scandium borates and their optical properties. And today we present new scandium samarium scandium borate doped with various lanthanides and their optical properties. Crystals with the general formula which shown in slide. They all are pixel monoclinic crystal. We studied the influence of dubbing of various lanthanide on absorption, luminescence, and second harmonic generation response. First, absorption. Absorption spectra are presented showed there is no all absorption bands for samarium as well as other lanthanides are shown and absorbed and labeled to their characteristic transition absorption. We observed that there is no shifting or changing for samarium bands, and the most the characteristic most intense band for samarium are located at 405 nanometers. Then the luminescence for all crystal were reported, or all they all have the same spectral, excepting for crystal doped with europium. It's because europium itself have a high luminescence when exciting when with 407 nanometers. Generally, there is no changing in spectral and the normalized spectra, but we observed that dubbing with lanthanide with higher atomic number leads to lower samarium fluorescence intensity. Then, to study the second harmonic generation response in this crystal, we choose the simple test, Kurtz and Berry powder test under the pumping of neodymium YAG laser, and we choose the LBO crystal to compare our results. and using this formula to evaluate the to calculate the nonlinear coefficient, the effectiveness, all crystals were refracted in the in fractions from 20 to 200 micrometers. For all crystals, we see so the characteristic depending on of second harmonic generation intensity on the pumping intensity as well as LBO. And for all crystals, we see increasing of second harmonic generation intensity with increasing of the particle size, which means that all crystals are phase matchable. For all crystal, there is a second harmonic generation response comparable to LBO, excepting a crystal with gadolinium. But on this stage, we can't. We don't have enough information to explain this behavior. We have to know the point group and the point group and the compounds and unit cells parameter to better explain this behavior. In conclusion, there's we reported new samarium scandium borates doped with various lanthanides. They all pixel monoclinic crystal. There's dubbing with lanthanides don't affect on spectral on absorption and luminescence spectra, just with higher atomic number leads to lower samarium fluorescence intensity, and there's we have to more investigate of the more information about the unit cell and point group to determine the dependence on the second harmonic generation pattern. Thank you for your attention.
Any inquiry?
Thank you very much for your presentation. And do you see the specific absorption of rare earth ions which you add to your crystal? You add different rare earth ions to your crystal.
Yes.
And do you see their specific absorption bands?
Yes.
All of them are characterized by absorption bands.
Yes.
Do you see them in the spectrum?
Yes. Yes. All absorption bands are here in this for samarium and for the new dubbed lanthanides. So that that we can say that dubbing with these lanthanides don't change the samarium absorption. Okay, thank you.
You are currently the only person in this conference.
какое-то стекло, которое будет в обратную сторону. Ну, колосин это как класс, но он такой, который будет наоборот сжиматься уже в тот момент, когда в тот момент у вот этого стекла сердцевины достигнет максимум, его должен быть уже, ну, не минимум, а сильно сжаться. Все равно, что
You are currently the only person in this conference.
Супер. Так, у нас как? Ну, я вам запущу.
Так, там вчера был проблема. На какую кнопочку нажимать, кажется.
Если он выключен, то включаете его. Флешку можете забрать. Турбин, да?
Good afternoon, all. Yeah, so I'm Prachi Sharma. I'm a session chair for this session. So I would like to invite K. Pierpoint from Porkhorov Journal Physics Institute, Moscow, Russia.
Good afternoon, everyone. My name is Ksenia Pierpoint, and I would like to present you the results on spectroscopic properties of chromium ions in zinc manganese selenide solid solutions. The work was done by the researchers from Prokhorov General Physics Institute and from Czech Technical University in Prague. So I will tell you something about the motivation of our research, the samples, and get you know the results we obtained and make some conclusions. So the chalcogenide solid-state materials doped by divalent transition metal ions find wide applications in optical communication, medicine, spectroscopy, laser remote sensing of the atmosphere, and many others. But the advantages of chromium ions in A2B6 materials, in particular zinc selenide, as most widely studied, include very broad absorption and emission spectra, high cross-section, negligible excited state absorption, and relatively long lifetime, which is almost independent of temperature. These features are very important for the development of infrared lasers based on chromium. And basically now, so far, chromium lasing around 2.5 micron was demonstrated in a variety of A2B6 materials, such as zinc sulfide, zinc selenide, cadmium sulfide, cadmium telluride, and many, many others. But present research activities are focused on finding probably new dopant host combinations or modifying current situation. So one of the ways to modify chromium ions in zinc selenide is by using solid solution approach. So this is one of the examples of such compound, zinc manganese selenide, ternary compound semiconductor that offers the possibility of modifying and optimizing chromium optical properties as a function of chemical composition and lattice parameter. As you can see in the figure, it already demonstrated itself as a prospective laser media, and it was shown that laser wavelength is longer compared to zinc selenide, which doesn't contain manganese in the compound. So this picture was taken from the reference mentioned in the slide. But by far, there was no extensive investigation of chromium spectroscopic properties in such compounds as a function of manganese content. So this was the aim of this work. We investigated chromium ion spectroscopic properties in cubic solid-state solutions because up to 40% of manganese, zinc manganese selenide, holds zinc blend structure, which is similar to zinc selenide. Concentration of chromium in our samples was very low, only about 3 by 10 to the power 18 per cubic centimeter. Samples were synthesized by vertical Bridgman technique in graphite crucible under inert gas pressure. And then our samples were cut from the bowl and polished on two sides. The thicknesses of the crystals were 2.2 millimeters for zinc selenide and about 3 millimeters for other samples. The samples were provided by Institute of Single Crystals in Ukraine. So now in figure 1 you can see the absorption spectra for samples with 0, 10%, and 40% of manganese, revealing a quite stable shift of maximum of the absorption spectrum towards longer wavelength. To fit these spectra with Gaussian lines, we have to represent them on the frequency scale. So here you see the examples of absorption spectra on the frequency scale for 10% and 40% of manganese, together with their fit by Gaussian curves. You can see that they can be well fitted by a single curve with close line width and different central positions. We carried out this approximation for all our samples and summarized the data in figure 3. You can see that the absorption maximum shifts towards lower energies, towards longer wavelengths with increase in magnesium content at a rate of about 30 inverse centimeters for every 10% of manganese. Here in the figure you can also see lattice constants, also revealing an inverse linear trend. The constants were taken from the references here. Next, we studied fluorescence spectra. So here you can see the spectra for 0% and 40% of manganese. Also, you can see that the maximum of fluorescence spectrum shifts compared to the sample not containing manganese. We also fitted it by Gaussian curves following the configurational diagram, which is shown on the slide. It was taken from the reference. So you see that both curves presented for 10% and 40% of manganese can be well approximated by the sum of two Gaussian curves with different central positions and different amplitudes. We carried out again this approximation for all our samples under investigation and summarized the data for the maxima of both fluorescence lines. In the figure, you can see that we observe the same kind of trend, 30 inverse centimeters per 10% of manganese decrease in the wavelength, in the wave number, say. So we suggest that this is caused by the decrease in crystal field strength due to higher lattice parameter and lowering of the 5E configurational curve. Next, as I said, chromium iron's advantage in A2B6 materials, one of the advantages is a very stable lifetime. So we studied lifetime in a wide range of temperatures. And here are samples for temperature 77 Kelvin for two samples with 5% and 30% of manganese. As you can see, even though the concentration of manganese is 6 times higher, the lifetime is almost the same, 5.6 microseconds and 5.3 for 30% of manganese. And in figure 8, you can see the temperature dependence we obtained for our samples. So here represented only 3 curves, and you see that lifetime drops with temperature at about 240 Kelvin for 40% of manganese and above 300 Kelvin for 5% of manganese. We think that this is due to the narrowing of the delta E gap between the bottom of 5E configurational curve and the intersection point of 5T2 and 5E curves. To check our assumption, we calculated the non-radiative decay rate using the equation from this reference. And in figure 9, you see by dots our obtained values for non-radiative decay rate. Now, to find the delta E gap, we carried out approximation of our experimental dots using this equation, also from the same reference. In the figure, the approximation by this equation is shown by dashed lines. And in figure 10 are presented the values of delta E gap. You can see that it narrows almost linearly by 400 inverse centimeters per 10% of manganese. So I'm already at the conclusions. We studied the spectroscopic properties of chromium ions in zinc manganese selenide solid solutions having cubic structure. The maximum of both absorption and fluorescence spectra move almost linearly towards longer wavelength at a rate of about 30 inverse centimeters per 10% of manganese. The shift is suggested to be caused by the decrease in crystal field strength due to larger lattice parameter and lowering of 5E chromium ion level. And the lowering of the 5E level position also results in stronger fluorescence time non-radiative quenching. So this is what we found. Thank you for your attention.
Thank you for providing the insights of the chromium ion. So any questions? Okay, so one question from my side, like you limit it from 0 to 0.5. Is there any limitation or it keep on linearly increasing?
Sorry, from 0 to 0.5?
0.4, you maintain the x as 0.4. So
Yeah.
is that any limit we need to maintain?
Yeah, so 40% of manganese is kind of like cutoff point for a cubic structure, because above 40% of manganese, it turns to Versite lattice structure.
Oh, thank you.
And it can be different.
Got it. Thank you. Thank you.
Okay. Thank you.
Okay, next I would like to invite A. Tobin from Samara branch of the Lebedev Physical Institute, Russia.
Так, Паша где?
Good morning, dear colleagues. My name is Tobin Alex. The name of my topic is presented in the slide, but I need some outline. I have a mission for this topic today, and it is included in slides 3 and 4. And after that, I will talk about some recent results. I'm working in Samara branch of Lebedev Physical Institute. It was founded by direct participation of Nikolai Basov, and the idea was to create the scientific laser research institute in the manufacture center. I'm working in the laboratory of physical chemical kinetics, and previously it was called the laboratory of electric discharge chemical and electric discharge generators. My topic, the name of my topic is the role of rate constants, and the main sphere which we are doing in our laboratory is measuring of the rate constants of the processes involving electronically and vibrationally excited molecules and atoms. The very common question which I get at all lasing conferences is why are you measuring rate constants? What for are you doing it? And today I'd like to in 2 slides explain what is it. The rate constant is the physical value which connects the rate of change of some, which connects the temporal dependence of the population of upper or bottom lasing level, for example, with the concentrations of other reactants, such as it is shown in the, oops, no? So it is shown in the left. The rate constant, the typical expression, I know that is obvious for many of them, but it is expressed from the Arrhenius equation, which is, has a strong dependence on the temperature. In typical laser, and especially in gas lasers, which we are working most of all, the concentration, the number densities of upper and bottom lasing levels is described through the through populations of them. In gas, the energy transfer molecule or atom is the atom, and it or molecule, and it reacts in the gas phase. That's why if you want to build an accurate model of the lasing active medium, you have to know the rate constants. In our laboratory, we were working for many years for developing gas lasers such as oxygen iodine laser, or optically pumped alkali vapor metal lasers, and for today the hot topic for us is the optically pumped rare gas laser. I heard yesterday one topic on this about this laser. Today there will be 2 more. So I'm glad to hear it. Talking about oxygen iodine laser and alkali, I won't talk too much. I'll just show the some rate constants which we measured since in last 7 years, and we used different methods to do it. But the hot topic for today for us is the optically pumped rare gas laser. What is it? In 2 words, this laser is very similar to alkali vapor metal laser. The active medium of it is consists of the heavier noble gas atom in metastable state in the mixture of light noble gas atom, for example, helium. The lasing was observed at all kinds of heavy noble gas atoms. How it works? The metastable atoms are produced in the electric discharge, which populates the level S5 of the noble gas atom. The optical pump populates the level P9 or P8. Then the upper lasing level is P10, and the lasing population is at the transition P10 to S5. The development of this laser today is suppressed, first of all, without knowledge of the rate constants of the energy transfer processes in it. That's why for today, for us, is the main aim is to measure the temperature dependencies of the rate constancy in to start with, we decided to investigate the mixture of argon and helium. We constructed the model, we built the kinetic model to determine the rate constants. Models created earlier took into account only levels which participate in the lasing cycle, but our experiments showed that if at intense pumping of the P8 level, the higher levels P7 and P6 are populated too, and we have to take them into account. These investigations are also necessary because one of the paths to increase the efficiency of the laser is to use double pumping from first pump from from S5 level to P9, and During lasing cycle, the S4 level is also populated, and the suggestion is to use the second laser pump to higher level, for example, to P8 or P7. The question is not solved for today. Here in this diagram, I show you the laser cycle, it is to the left, and the transitions which are used in the experiments. The violet arrow is the pump in the experiment, and the green lines are laser-induced fluorescence, which we see. The kinetic model was built in using the COMSOL multiphysics, the module reaction engineering. It included near 40 reactions and energy transfer processes. This model, in fact, is the system of the differential equations, but it doesn't have an analytical solution because of the principle of detailed balance. We have to take into account the reverse processes. That's why the only way to get the unknown rate constants and the temperature dispenses is to customize the rate constants and to get the nice agreement between model and experiment. Here is the experimental setup for measuring the rate constants in our lab. The mixture which we prepared is the argon-helium mixture with 1% of argon in it. The discharge was ignited inside the vacuum chamber in a volume 500 cubic centimeters. The discharge ignited between two titanium electrodes. The geometric dimensions are 40 millimeters left, width 2 millimeters, and the inner electrode space 3 millimeters. To pump necessary wave levels of the metastable, we used the tunable Titan Sapphire laser with 10 it is a pulse laser, 10 hertz, and the pulse duration near 10 nanoseconds. The induced fluorescence was collected simultaneously by 3 channels, and that's how we avoided the fluctuations between the amplitudes of signals. The emission was collected by lens, transferred to monochromator, and recorded using photomultiply tubes, high speed with time response below 1 nanosecond. That's all common things, but in the main advantage of our experimental approach is that we can measure the temperature in the gas of inside the discharge zone using a tunable diode absorption spectroscopy method. The emission of the diode laser passes through discharge zone perpendicular to the lone side and goes to the receiving photodiode. Part of the emission of the photodiode creates the reference channel, and as a result, we can observe the absorption bandwidth. It can be easily approximated using Voigt function, and according to the broadening of the Voigt function, it has the temperature dependence. We receive the temperature of the gas. Moreover, all necessary broadening coefficients for argon were also measured in our laboratory, and as an example, here you can see typical signals which we receive simultaneously in the experiments. These results were received at the P8 level pump, and the P7 and P6 lie over the P8, and we still see them. The smooth line on the graphs is the results of the modeling with this total coefficient, rate constant coefficients of the total quenching. You see the perfect agreement between experiment and the model. Practically the same rate constants can describe another case when we use the P7 pumping, but the only difference is connected with the total quenching rate constant for P7 state. It is more than 3 times lower than in previous case. The main difference in we try to understand what's the problem in it. The real problem, as we see, is that the pumping line S5 P7 is at high pressures over 100 torr, practically overlaps another line in argon. It is the line P2 S2, which makes some mistakes in gives us a mistake in the determination of the rate constants. So the main conclusion of this part of the experiment is not to use the P7 pumping. The previous approaches in this case of measuring rate constants was so that we don't need the ratio between the amplitudes of the signals. But our first modeling and comparison with the experiment showed that it is not true. We need to know we need to calibrate channels and to know exactly how much each signal is more than another signal. So we carried out the calibration using the calibrated light source, and here the signals are recorded using calibrated channels. Again, we see perfect agreement, practically perfect, but these rate constants, we trust them more. Another advantage of the calibrated signals is that we can now estimate the branching fractures. So where exactly the high level argon quenches at P7 or at P10, that is maybe the most important part in the modeling of this active medium. If we repeat this procedure at different temperatures and pressures, we receive the time dependencies of the rate constants. Here, just an example of such a dependence. We see nonlinear dependence. In several cases, it has some strange behavior, but it is just the first results. They even are not approximate yet. We need to carry out new experiments with more signals, especially we need the signal from P10, and now in post-deadline, we organize the 4th channel with P10 level. That's practically all I wanted to tell you about. If you have any questions, please don't hesitate to ask me. And
thank you. Thank you for the wonderful presentation. So any queries, questions?
How did you calculate the electron energy distribution function?
Again, man?
What?
Can you repeat?
How did you calculate the electron energy distribution function?
In our research, we did not, but we did not calculate the electron energy. It is we are modeling just the kinetics so how the reactions can take place in the active medium. So it was another part of our research. The model of the discharge was carried out in another work.
Will you do the same experiments with the krypton?
We are planning it. The wavelengths are practically the same. So first we make mistakes on argon, and then we can carry out them on krypton. Argon is cheaper.
Thank you.
Thank you for report. Where can I read your results more carefully? Have you published it?
They are not. There is one in bulletin of Lebedev Institute, one result, but our fresh results are not published yet. We are collecting information about time dependencies. About lasing, I know about lasing on argon. There is the work in express optics. Yes, correct. Yes.
Optics Express?
Optics Express, yes. It is about, it is the work of
Thank you.
20.
Any other question? Thank you. Okay, now I would like to invite S.A. Solokin from Kovrov State Technological Academy, Russia.
Можно, да? Sorry, I have to do this talk. I'm co-author, Sergei Smetanin. The work was done in 3 institutes. High power, high efficiency, neodymium YAG laser, continuous wave mode locked with CVD graphene. Graphene synthesis was done at Moscow Institute of Science and Technology. Characterization and first mode locking experiments were done at Prokhorov General Physics Institute. And final development of laser system was done at the Kovrov State Technological Academy. Ultra-fast mode-locked lasers have widespread applications in many different fields, such as medical applications, biology, microscopy, many, and so on. Recently, graphene-based separable absorbers are drawing more and more attention due to its unique properties, such as wideband tunability, fast separable absorbability, and simple and low-cost fabrication. Usually, graphene mode-locked solid-state lasers have low average power, lower than 1 watt, or low optical efficiency, lower than 10%. The highest output average power of neodymium YAG laser continuous wave mode locked with graphene was as high as 2.1 watt, but optical efficiency was low, 4.9%. It is because of optical damage of graphene separable absorber. To date, the highest optical efficiency of graphene mode-locked solid-state laser with 1 watt level output power is 16.2% for neodymium-doped yttrium vanadate. Further increase in power characteristics was limited by thermal load of the laser crystal. In the present work, the laser design has been improved for higher power operation, high power, high efficiency diode and pumped neodymium YAG laser with continuous wave mode locking by single layer CVD graphene is experimentally investigated. Output radiation at 1.064 micron with average power of up to 1.7 watt at optical to optical and slope efficiencies of 19% and 24% respectively were obtained. Okay, characterization of graphene separable absorber. Raman spectra shows that 2D band of is about 2 times higher intense than G band, which is known as a fingerprint of graphene, unlike other carbon materials such as graphite or carbon nanotubes. D band has not been noticed due to the absence of defects in the graphene sample. The tight peak shape of 2D band, 35 inverse centimeters bandwidth, confirms that the sample is a monolayer. Whereas the multi-layer graphene shows a specific increase in the 2D band. Transmission spectra show that we have about 3% absorption of lamp intensity in the wide range of lamp light, which is another confirmation that the studied graphene is the monolayer. Why monolayer? Monolayer has the lowest losses for operation as an intercavity element. So we can obtain the highest efficiency of oscillation in the mod-locking regime. And also we applied the graphene monolayer directly on the laser mirror. To decrease losses, we obtained the highest efficiency at high power. But we have one problem for that. If we use monolayer, we have the lowest modulation depth of saturable absorber of about 1.5%. But we used a special construction of laser cavity. The calculated cavity to have long length at the end of stability diagram to obtain stable mod-locking regime using saturable absorber with low modulation depth, monolayer of graphene. You can see experimental setup. It is usual setup. Graphene monolayer is applied directly to end mirror, and we optimized construction, and we used enough low beam spot. It is 20 micron for operation of graphene as a saturable absorber. And the spot in the YAG active element is of about 200 micron. It is good for multi-mode diode pumping. We used continuous wave diode pumping, 10 watt. And matching of beams of pumping and oscillating beam resulted in single mode operation of the laser. So this is demonstration of stable continuous wave mode locking oscillograms. We can see the first oscillogram demonstrate it in at 10 microsecond scale, all scale. So it is stable regime, but it was obtained at some conditions. So this is output characteristics. We can see on the figure on the left linear growth of output average power, but at pump power slower than 5 watt, the mod locked regime was Q-switched. At pump powers higher than 5 watt, we obtained stable continuous wave mod locking regime with the very high slope efficiency of 24, exactly 24.5% slope efficiency. Maximum output average power was 1.7 watts. But at pumping power higher than 9 watt, we had no growth after these higher pumps. We think it is about not only thermal lensing in the active elements, it is because our cavity is at the edge of stability diagram. So thermal lensing is very strong effect here. We didn't observe optical damage of monolayer of graphene. We decrease power back and they obtain the same power characteristics of the laser. Figure on the right demonstrate stability of operation at 9 watt input power. Instability of 2% was realized. So pulse energy 21 nanojoule is obtained for this laser. It is the most efficient graphene locked solid state laser to date. We measured pulse duration. It was of about 39 picoseconds in the after correlator scheme. Okay, summary. High power, high efficiency diode and pumped neodymium YAG laser with continuous wave mod locking by single layer CVD graphene is experimentally investigated. The highest output average power of the laser was as high as 1.7 watt at 9 watt pumping. In continuous wave mod locked regime at optical to optical and slope efficiencies of 19 and 24% respectively. The highest individual picosecond pulse energy was as high as 21 nanojoule for a repetition rate of 82 megahertz at pulse duration of 39 picoseconds and diffraction limited beam quality. Increasing the pump power higher than 9 watts led to decreasing the optical efficiency due to a thermal lens in the neodymium YAG crystal. Thank you.
Thank you. It's a wonderful presentation. Any questions?
I have a question about the slide number 6. Could you please show the slide number 6? And just what is the Q-switched mode locking regime? What are the pulse characteristics in this regime?
Q-switched mod locked regime, it is repetition of trains of ultra short pulses with different repetition rate, and if we have near threshold operation from of about 2 watt input power, it is unstable, really unstable, but we only can observe ultra short pulses in some unstable trains. But increasing the pump power led to operation of pulse trains with several pulses inside. This regime is unstable from 1 to 2nd operation. We didn't get the same characteristics in this regime if the power is lower than 5 watts. Only if power is enough high input power, we have stable regime. So it is an unstable regime Q-switched.
Thank you.
Any other query? Okay, thank you so much. Yeah. So next we have with us SN Skolo from Inject Limited, Russia.
Ручка. Так, красный это лазер. И вправо. Ваша, да? Good afternoon. Let me introduce you my talks. Prospective laser and optoelectronics component and the applications. Two words about Inject. Inject is electronics enterprise placed in Saratov city. We have 500 people in staff, and we make research and development and industrial production of semiconductor laser diode. I show you brief report about high power semiconductor lasers and their application in the industrial field and perspective in this area. To apply these lasers, we designed some laser diode models coupled in fiber. Typical picture you can see here, there are some samples of such lasers. The highest power is in continuous wave 400 watts. Typical wavelengths in 940 nanometer, and we couple the emission of several LD bars in one fiber with core diameter 800 micrometer. The highest power is about 400 watts. There are several models for pumping of fiber laser. In this case, we receive typically 900 watts and 100 micrometer, and also about 200 watts in fiber with core 200 micrometer. With wavelengths 975 nanometer, it's typical for pumping of fiber laser. The main problem which we solve, how can we apply high power laser in industry to increase lifetime of machines and mechanical parts. Main area application, machine building industry, shipbuilding industry, aviation, and so on. You can see here some industrial setup on the base of high power laser PLD6 with output power about 6 kilowatt in continuous wave with white light beam spot on the surface of treatment part. You can see here laser head installed in robotics arm, Fanuc robots, and some parts treat using of this machine. No, there are several parameters, 6 kilowatts, wavelengths in bandwidth 800, 980. The port diameter is 22 millimeter up to 2 millimeter without homogenizer, and efficiency of this setup, it's about 30%. No, it's power supply with laser beam models. Laser models coupled in fiber, and with this fiber, we couple all emission in this emitter laser head, and there are several power supply. Now, in the result of application, we received increasing of lifetime about 200–400%. This machine placed in St. Petersburg tractor plant. You can see here this industrial workshop and some gears treated with this laser. Now you can see here the data of this heat treatment. It's locally we increase hardness of this part made from steel. Typical steel it's 40X, 40H. It's increasing was from 15 Rockwell units up to 60 Rockwell units. The depth of heat treatment, it's about 1 millimeter up to 2 millimeter really. its beam profile on the surface of this part. You can see rather non-uniformity. No, this is the results with some test samples. I have also picture, video, but I think it's, oh no. Yes, you can see here heat treatment real shaft from plunger pump. This is the real process of hardening. We don't need some additional after treatment processing and some liquids and any additional treatment. This part can be used after this treatment immediately. To increase this, the quality of parts, we designed and manufacture also homogenizer. It's quartz-made optical part on the base of cylindrical arrays. You can see here high uniformity, and we increase also in this case beam spot up to 32 millimeter per 10 millimeter. Also good uniformity of part after this heat treatment. The power was 408 kilowatts, velocity 5 millimeter per second, temperature on the surface 1180 degrees centigrade. This equipment and this setup can be used in many fields. First of all, I said this heat treatment, drying and some welding, maybe ceramics and other material, laser soldering, laser modification of surface, doping, it's hot, I don't know English name, броня, to produce hot surface. And also composite manufacturing and scientific research. To make some cladding, we need additional equipment. In this case, we need powder feeder and some special, where is it? Special nozzle. It's a slit nozzle because we have not round shape, small part, a small spot on the surface. We need some white feeder, so we need special design nozzle. Yes, and other equipment is the same. Now you can see here typical process of cladding with this nozzle. Now some test parts made on this process. We cover steel 40X with stainless steel powder. No, also, the width of this cladding layer was about 22 millimeter. Very interesting application. It's heat treatment of composite prepreg thermoplastic covered with thermoplastic material with laser. I think it's very bright, very useful technology which can be used for large-scale production of composite material and composite parts. This technology is widely used in foreign countries, but in Russia it's on a first step of application. No, typically we need heat some area near the placement of prepreg tape. This prepreg tape covered with polyfluorophore ketone material, and we have some testing of this technology. We use this machine, PLD6, with white beam spot. But in this case, the temperature, we need to heat the surface only for 400 degrees. But if the velocity of placing is high, we also need to use 4 kilowatts output power. No, here I have some parts. It's rather hard. Можно выключить меня там. Excuse me, my telephone. Also, we try to use laser models with low power. It's some typical industrial technology. It's soldering, laser soldering. You can see here Japanese prototype of this machine. It's rather simple, but very expensive. No, we designed, and now we are designing, and we applied this technology to industrial kind of machine for microelectronics. We use laser with heat treatment about 20-30 milliseconds with high density of assembling. The output power in this case, it's not so high. It's only 80 watts in continuous wave or pulsed. No, wavelength is typical for laser models and high efficiency. It's about 970, but we can use 800 or red. It not depends, but for technology we need about 100 watts. So this machine is automated with some wide treatment area. No, we can make a different kind of beam spot on the heat treatment parts. The same machine, but with high power. We can use also for plastic soldering. No, it's attractive technology. In this case, we can solder two parts together, black and transparent plastic. Also, we can solder it white to white plastic, but it's rather hard. We need, in this case, more power, and it's not so easy. No, in literature you can find a lot of plastic which can be soldered together. It's rather useful information. No, typical parts which can be soldered. Mostly it's these parts applied in aviation, in some automotive industry, and so on. Also, we produced typical two-dimensional laser diode arrays for pumping of solid-state laser and another type of lasers. You can see here some information about diode pumping LD array, specially designed for pumping solid-state laser, which don't need some thermostabilization, because in this case, we make laser arrays with different wavelengths, with wide emitting spectrum, which can be used without thermostabilization. We have more power and we don't need thermostabilization. In this case, we received so-called athermal laser. So it's possible use without special thermostabilization system, and it's compact and attractive in this case. Also, we designed some very high power two-dimensional array for pumping some cryogenic laser, for laser fusion, for instance, or some 50 kilowatts laser emitting arrays for some illumination, maybe also for pumping, for some scientific research areas. Also, we can present some primary results in the field of laser shock peening and this application. On the base of research program Russia-Belarus, we produced some prototype of industrial machine. It's high power diode pump solid state laser system with output energy about 5 joules and with frequency up to 11 Hz, laser pulse duration about 13 nanosecond, beam core it's about 20 millimeter, beam divergence 2.5 millirad. You can see here the emission beam. No, for us it's very interesting application. No, In some other countries, they use a lot of such research system in wavelengths, typical solid-state laser 1064, 532, with output energy up to 200 joules and frequency up to 50 nanosecond, up to sometimes 500 hertz. No, but really it's very difficult problem. 2 words about principle. We use this explosion in the surface of parts which covered with water typically, and we received high shock treatment for many material. In case in case of this application, we received lifetime increasing of lifetime up to 20 times, and the depth of this treatment zone will be up to 12 millimeter. It's very attractive for many applications, but the problem is very difficult. No, also some pictures illustrate application of this system. It's treatment of laser weldings, laser welds in some ships. Also aviation, the same process for aviation. Laser shock marking, it's attractive process which don't use some ablation. So we don't make some treatment of surface, only shock pinning without ablation. Laser impact embossing. This is laser pin texturing. Also some interesting nano imprinting, also interested in microelectronics and nanophotonics. Also, we can make some treatment of ceramic material, increase this this is some parameters. Now, in the results, the lot of laser technology can be used in industry, and 10 years ago, some experts estimate economics effect of this application up to 100 million rubles, but it was 10 years ago. Now I think it's 10 times more. Thank you. This is the end.
Any queries? Do you have any question? No, I'm just. Okay, thank you.
Thank you.
Pardon?
Sergey, I'm interested. How many machines did you solve for which applications? Сколько машин вы продали и каких?
We designed pumping units mostly, but we sell our laser source to some other company which make installation. No, in the total, maybe in 5 years, we sold about 3 setups. A tractor machine built a factory in St. Petersburg. It's hardening of gears, mostly this application. And now we make some original process in our facility, in our workshop. We designed special workshop with heavy industrial machines, some robotics, and some rotator up to mass 1 tons, because it's heavy industry. It's not small microelectronics. We use laser in heavy industry already.
So now I would like to invite V.A. Shaidulina from FSUE Sarov, Russia.
Здравствуйте.
На стрелочку, да? Переключать на стрелочку. Переключать. На стрелочку.
А кликер кто забрал?
Все, вот он, здесь. Здравствуйте, меня зовут Шайдулина Валентина, я сотрудник ФИАТ СНИЕФ город Саров. Представляю вам доклад на тему лазерная генерация на метастабильных атомах криптона с оптической накачкой. Целью данной работы являлось исследование лазера на метастабильных атомах криптона. В рамках проведенной работы была получена лазерная генерация на метастабильных атомах криптона, измерена ее мощность и создана кинетическая модель криптона гелиевой плазмы для изучения характеристик параметров активной среды лазера. Лазер с оптической накачкой на инертных газах – это новый тип газовых лазеров, преимуществом которого является высокая удельная мощность. Предполагается возможность получения до 500 Вт с кубического сантиметра активной среды, высокий квантовый КПД, однородная химически инертная активная среда. Предполагается использовать лазер для преобразования мощного диодного излучения с низким качеством пучка в мощное излучение газового лазера с высоким качеством пучка. Для получения лазерной генерации используются возбужденные состояния атомов инертных газов. В нашей лаборатории к настоящему моменту была получена лазерная генерация на аргоне мощностью 4,11 Вт. В данной работе при проведении экспериментов в качестве активной среды использовалась смесь из криптона и гелия. На слайде представлены энергетические уровни атома криптона, участвующие в лазерном цикле. Нижний лазерный уровень 1s5 заполняется при прохождении импульсно-периодического разряда. Уровень накачки 2p9 заполняется при поглощении атомами на уровне 1s5 излучения накачки на длине 811 нанометров. Верхний лазерный уровень 2p10 заполняется посредством безизлучательных столкновительных переходов с уровня 2p9. Генерация лазерного излучения на длине волны для криптона 893,1 нанометр происходит между уровнями 2p10 и 1s5. Для наработки метастабильных атомов криптона или другого инертного газа используется импульсно-периодический разряд. Значения напряжения и силы тока, измеренные в процессе эксперимента, представлены на слайде. Амплитуда напряжения составляет 1800 вольт, амплитуда силы тока 6 ампер. Разряд имеет длительность 40 наносекунд по полувысоте и частоту повторения 80 кГц. На слайде представлена фотография межэлектродного промежутка при прохождении разряда. Использовались электроды, изготовленные из танталовых и вольфрамовых лент. Электроды представляли собой параллельные плоскости размером 3 на 15 и были расположены в 3 на 3 мм друг от друга. На данном слайде представлена схема эксперимента по получению лазерной генерации на метастабильных атомов криптона. В качестве источника оптической накачки использовался диодный лазер на длине волны 811,3 нанометра мощностью 130 Вт. Генерация была получена при атмосферном давлении в кювете и расходе 3 литра в минуту. Газовая смесь при этом состояла из 96% гелия, 2% неона и 2% криптона. Оптический резонатор состоял из плоского выходного зеркала, сферического глухого зеркала, радиусом кривизны 50 см. Значение коэффициента отражения для сферического и плоского зеркал на длине волны генерации составляли 99 и 87,6% соответственно. На слайде представлена полученная с помощью монохроматора запись спектра, на котором видна полученная линия генерации криптона на длине волны 893 нанометра и рассеянное излучение накачки на длине волны 811 нанометров.
Мощность лазерной генерации на метастабильных атомах криптона, полученная в этом эксперименте, была измерена с помощью оптического калориметра и составила 30 милливатт. Для дальнейшего исследования лазера была разработана кинетическая модель криптона-гелевой плазмы. В модель включены возбужденные атомы криптона в 5 энергетических состояниях. Это нижний лазерный уровень 1s5, верхний лазерный уровень 2p10, уровень накачки 2p9. Уровень накачки 2p9 и 2 дополнительных уровня 1s4 и 2p8. Помимо этого в модель включены атомы криптона и гелия в основном состоянии, ионизированный атом криптона, молекулярный ион, оксимер, атом гелия в возбужденном состоянии и ионизированный атом гелия. Для сравнения с криптоном была создана упрощенная модель аргона-гелевой плазмы. Кинетика модели с аргоном рассматривает взаимодействие тех же энергетических состояний атомов, что и кинетика модели с криптоном. С помощью моделей криптона-гелевой и аргона-гелевой плазмы было проведено вычисление концентрации метастабильных атомов в различные моменты времени. На слайде представлена динамика увеличения концентрации в течение 3 периодов разряда. Полученные результаты позволяют сделать вывод о том, что для получения одинаковой скорости возбуждения метастабильных атомов в криптоне требуется на четверть меньше напряжения разряда по сравнению с аргоном. Это объясняется тем, что энергия возбуждения энергетического уровня 1s5 в криптоне на 14% меньше по сравнению с аргоном. Таким образом, использование криптона в качестве лазерной частицы позволяет существенно снизить КПД, повысить КПД разряда. Для получения наибольшей концентрации метастабильных атомов необходимо создавать смесь с оптимальным значением доли криптона. На слайде представлены результаты вычислений концентрации метастабильных атомов для различных значений доли криптона в смеси. Значения концентрации нормированы на максимальное значение. В качестве входного параметра расчета использовалось напряжение, измеренное при проведении экспериментов. Результаты расчета позволяют сделать вывод о том, что оптимальная доля криптона в смеси составляет приблизительно 3% для экспериментальных условий. Данное значение может изменяться при изменении параметров разряда или параметров активной среды. В результате выполнения работы была получена лазерная генерация на смеси криптон-гелий на длине волны 893,1 нанометр при использовании импульсно-периодического разряда и излучения диодного лазера в качестве источников накачки. Мощность полученной генерации составила 30 милливатт. Создана кинетическая модель криптона-гелевой плазмы и проведено сравнение эффективности возбуждения метастабильных атомов на нижний лазерный уровень 1s5 для криптон-гелевой и аргон-гелевой плазмы. Таким образом, можно сделать вывод, что использование криптона в качестве лазерной частицы позволяет снизить напряжение разряда по сравнению с аргоном. Определена оптимальная доля криптона в смеси, которая составляет приблизительно 3%. Спасибо за внимание.
Any questions?
Скажите, пожалуйста, вот у вас там смесь была, добавка неона 2%, да? Что это дает вообще в эксперименте, как это, так сказать, сказывалось?
Предполагалось, что это позволит снизить пробойное напряжение. Это тоже в качестве эксперимента еще... То есть просто было предположение, что это поможет снизить пробойное напряжение и увеличить КПД. То есть это...
Any other? Okay, thank you.
Спасибо.
So now I would like to invite P. Mikhail from Samara branch of the Lebedev Physical Institute, Samara, Russia.
Так, где еще раз ваша? Где ваша?
Good afternoon, dear colleagues. My talk is about optically pumped rare gas lasers, and I'll give you a brief review of the current state of the art. Motivation, of course, is the development of a high-power laser system which can outperform solid-state systems when the power management and the heat management and optical damage becomes important. I think I can omit most of this slide because of the previous reports. I only would like to say that this laser system was proposed by Michael Heaven from Emory University, and the first paper was published in 2012. And after that, it was extensively studied first in the United States, then by in our laboratory in Samara branch of Lebedev's Institute. Now I know at least two groups from China that study this laser. And in Russia, there are two groups, one from our laboratory and another from Sarov. And I only would like to add to the previous reporters that if you look at the laser output of this system for different rare gas atoms, all the lasing wavelengths fall in the transparency regions of the Earth's atmosphere. The bottleneck of the system is, of course, the energy transfer from the pump level to the upper laser level. The rate constant for this process is quite high. That's why this system is so interested. Just we can perform simple mathematics here, and if we have number densities of metastable atoms in the region of 10 to the 13 or even 14, which were obtained in recent experiments by the Chinese groups, we can easily estimate that the power that we can extract from 1 cubic centimeter of this laser medium is very high. Small signal gain is about 1 inverse centimeter, and this system is analogous to diode pump alkali laser. The kinetics is similar, and the gain is similar, and so I can cite these results. These systems were studied very extensively from the beginning of the years 2000, and they reported 1 kilowatt out of 20 cubic centimeters. That was the work by Sarov group. And 1.5 kilowatts were reported by the group from the Air Force Research Laboratory from the United States. But then there were no other publications, so we only can guess what happens now. So the simple three-level model, which takes into account collisional transfer and spontaneous emission, permits to estimate laser efficiency. The estimation is that laser efficiency with discharge requirements may be between 50 and 60%. So this system is very interesting for diode laser pumping, and of course the first question is how to pump this system, because the absorption width of the atomic lines is quite low. In the conditions of our experiment at an atmospheric pressure, noble gases produce lines with half width of about 10 gigahertz. But this problem was solved first for alkali lasers. This is research was done early in 2008, and recently by the Chinese group in 2016, as you can see. So they both use the so-called volume Bragg gratings, and that permits to make a diode pumping with a very small bandwidth of about 10 to 20 gigahertz. And just what should be the width of the laser pumping in our case? There are some modeling results for diode pump alkali laser. The absorbance bandwidth is nearly 20 gigahertz. So if you have a delta function or for diode pump bandwidth, or if it is half of the absorption line bandwidth, it's no difference at all. But if the bandwidth of the pumping radiation equals the bandwidth of the absorption line, you have something like 15% loss in laser performance. So the first successful experiment with lasing was done by with the help of a string of micro discharges. The micro discharges were produced by microwave radiation, and for the pump, the authors used a titanium sapphire tunable laser with a bandwidth as small as 2 gigahertz. So they have only 25 milliwatts of output, but they measured efficiency of 55%, which is close to what was estimated theoretically. And it's hard to estimate just how much power from cubic centimeters they extracted, but it is sure in the range of tens of watts from cubic centimeter. But the specific power load in the discharge was very large, in the range of kilowatts per cubic centimeter. And because these discharges were very small, their size was less than 1 millimeter, about 200 or 300 microns. So the question is how to organize discharge to efficiently produce metastables. So we performed these calculations and found that we need a discharge with E over N in the range of 10,000, which means that continuous discharge is out of question, because this parameter E over N depends on the production and loss of electrons. And these processes in the continuous discharge are governed by volumetric processes. So you can't do anything much about it. And in the continuous discharge, the E over N ratio is much smaller, something like here, 4 or 5,000, for example. But if you use a periodically pulsed nanosecond discharge, this discharge meets these requirements. It was shown by the modeling for argon-helium mixture. The authors modeled a discharge with time duration of about 20 microseconds, and you can see that just at the beginning of the discharge, the voltage is quite high. Electron temperature is also twice higher as after that, and E over N meets the requirement for efficient metastables production. And the first successful experiment with lasing in this type of discharge was performed The discharge was with duration of 300 nanoseconds at 200 kilohertz, and they obtained only 58 milliwatt output, but their number density of metastable argon atoms was as high as 1.4 to 10 to 13 in cubic centimeter. Also, the problem was found in this case. If you do not pump the discharge, it is totally homogeneous. But if you put your pumping laser near a node, the discharge loses its stability and becomes contracted, as you see. Another interesting discharge is dielectric barrier discharge. It also meets these requirements for high E/N values, and it's much more simpler to implement. And the trick is to make the dielectric barrier, which has high capacitance and at the same time can withstand high voltage without breaking. You see the discharge is also homogeneous, and these experiments were done at the frequency range of only 20 kilohertz. And we also obtained lasing in this case, but only at the middle part of the voltage for somewhere during 10 microseconds during the half period. And the number densities of argon metastables that were obtained in this case were only 2 to 10 to the 12, but that was enough to obtain lasing. And as you see, the voltage in this case is only 400 volts, and the currents are only just a little less than 100 milliamps. So if one can find a suitable dielectric layer with a high capacitance and which can sustain electric breakdown, this discharge will be very interesting for this laser. Another exotic approach to generating high metastable number densities is the so-called jet type discharge. You can see here that you can form plasma jet in this region. Just the central electrode and the outer electrode are in the glass tube, and if you apply voltage to those two electrodes, you can produce this plasma jet. And indeed, this group measured the number densities of the species of the lasing species of about 2 to 10 to 14 in cubic centimeter. Of course, the number density oscillated because the frequency wasn't high. It's something like 30 kilohertz, if I remember. And the size of this plasma jet is only about 1 millimeter. But if you pump it with a diode laser, you can obtain laser action, and they measured 100 milliwatts of lasing with help of argon metastables with 10% of optical efficiency. However, if you look at these graphs where traces of current and voltage are presented and multiply them, and you will see that the input power in the discharge was in the range of kilowatts. So, and also there is a problem how to scale this type of discharge. The other problem in this system is that if you start to pump the S5 level, you populate 2p9 level first, then because of collisions the 2p8 level also populates, and of course the upper laser level populates. After that, due to emission from these levels, spontaneous emission from these levels, the S4 level begins to populate. And at the same time, the 1S5 level depletes, of course. I'm talking about the pulse discharge, when the production and pumping are just not at the same time. So what happens after that? Of course, if you deplete the S5 level, the lasing terminates. But you have to there is a way to solve this problem. You have to apply additional pumping from the 1S4 level. You can pump it to 2P10 level or 2P8 level or even higher. In this case, you will depopulate the S4 level and return these atoms in the lasing cycle. And the experiments, recent experiments from Chinese group, just they showed this in experiment. The green trace is the population of 1S5 level without pumping, and the red trace is the population of this level when the pumping starts. You can see that this level is depleted, and here on this lower panel you can see that the population of the 1S4 level increases. And there is also an experiment with dual pumping. I know about only one such experiment. You can see these traces. This is lasing. The first peak is the interference from the discharge, and the second peak is when the radiation of a tunable dye laser was applied together with the main pumping. So evidently there is a very noticeable increase in power. And this panel shows what happens if you pump the 2P8 state or 2P7 state. And you can see that actually there is no difference, and the effect is very prominent. So, I made this slide before I heard the results from the group from Sarov, so I can just very happy to know that they also obtained these 4 watts for argon, and the lasing from Krypton system. And this is the results for Krypton with transverse pumping from one of the Chinese groups. You can see that the lasing ceases after about 2 microseconds. And in this case, where you implement argon metastables, the lasing is almost continuous. And here are the results for the lasing with xenon metastables. 350 milliwatts were obtained from xenon metastables, but the authors didn't measure the optical efficiency, unfortunately. So what are the prospects for different rare gases in this system? For example, for neon, you can see that there is a larger gap than for argon. So we can expect that the pH state won't be populated so rapidly as in the case of argon. And also the S4 state is much closer to S5 state. So we can hope that the relaxation of the state to the 1S5 will be faster. But unfortunately, for pumping of neon, we need a radiation with a wavelength of something like 640 nanometers. And the guys who produce lasers somehow just don't like this wavelength. In the case of Krypton, the P8 and P9 states are nearly coincide. The difference between them is only 13 reverse centimeters. That means that when you start to pump krypton, the 2p8 and 2p9 state, due to collisional transfer, they are populated almost equally. And so spontaneous emission to 1s4 state will be large. And the S5 state will be depleted quickly. And if you look at this panel, you can see that indeed that their lasing terminated quite fast. In the case of xenon, the 2p9 and 2p8 states change their places. This notation is historical. It was done before quantum mechanics, and the levels just labeled with increase of energies. So in this case, when you start to pump the former 2p8 state, which became 2p9, of course you raise the population quickly, and again this mechanism of depletion of 1s5 state will be profound, of course. Also, the 2p10 state is quite near to 1s2 state. The collisional transfer rate here might be fast. But on the other hand, xenon has a very wide, wider broad band of wide absorption line. In the case of these rare gases, the absorption line bandwidth is about 10 gigahertz or less. But in the case of krypton, the bandwidth is about 20 gigahertz, and in this case it's quite important. Also, I would like to mention that no or poor data about energy transfer rate constants and their temperature dependencies exist for all these atoms. And our recent finding was also that indicates that not all elementary processes in this system are known. Just here we studied the dependence of output laser energy on pump intensity in transverse pumping scheme. So you can see that at the left, for the left panel, we pumped the P9 state, and you can see that after the dependence exhibited maximum. So here some secondary processes appear that prevent the degrade lasing. The same dependence was when we pumped the 2p8 state. And in conclusion, I would like to state that despite that optically pumped gas lasers have a huge potential, the technology is not yet mature because we lack the data about the elementary processes, and we lack the experimental data about the interaction of discharge with intense laser radiation. And also, diode pump needs further development and improvement to achieve the narrow bandwidth. Thank you.
Please show the slide with the efficiency of discharge, maybe 7. How exactly the efficiency was calculated?
Solving loss equation and calculating Microphone. Well, it was calculated solving Boltzmann equation and just deducing how much energy that was input into discharge goes to excitation of the S levels. That's all.
How the energy of discharge was determined?
Oh, let's discuss these things afterwards, okay?
Okay, thank you.
Any other query?
Thank you for excellent talk. What can you estimate the overall efficiency of such a lasers? Not only optical.
Well, you see that this slide here, this is the estimation of the total efficiency with account for discharge requirements. This is the efficiency includes optical to optical efficiency plus discharge requirements, and you need about several tens of watts in cubic centimeter to sustain the acceptable metastable number density.
Any other question? Okay, so thank you for the wonderful presentation. We can end this session now. Thank you all for being a part of this session. Yeah.